Hello everyone. Welcome to Hexagon Tutorials. This is a beginner-friendly tutorial on Dart, a powerful programming language developed by Google. Dart is a versatile programming language used to build mobile apps, web apps, desktop applications, and even backend systems. It is the language behind Flutter, a popular framework for creating cross-platform mobile apps. Dart is fast, efficient, and easy to learn, especially if you're just starting out in the programming world. Now the question comes, why should you learn Dart? So here are the reasons why you should learn Dart. Perfect for mobile app development. If you want to build apps for both Android and iOS. Using a single code base, Dart is the way to go. Fast performance, Dart compiles into machine code, making your applications run super fast. Easy to learn. If you've ever worked with Java, JavaScript, or C, Dart will feel familiar. Even if you're a total beginner, don't worry. This course is designed to be beginner-friendly. Google-backed Dart is developed by Google and is used in many large projects, ensuring it has strong support and a bright future. Apps built using Dart and Flutter are Google Pay, Google Ads, Google Earth, Alibaba, and many more. Key features of Dart. Object-oriented, everything in Dart is an object. This makes it easy to structure your code. Hot reload. If you're building apps with Flutter, Dart's hot reload feature lets you see changes instantly without restarting your app. Asynchronous programming. With async and await, Dart makes handling time-consuming tasks like fetching data from the internet super simple. Cross-platform. Write once, run anywhere. You can build apps for mobile, web, desktop, and even servers with Dart. Memory management. Dart automatically handles memory, so you don't have to worry about it. Let's start our Dart journey. Variables and data types. A variable is like a container that holds a value. In Dart, you need variables to store and manipulate data in your programs. I will use Dartpad Online IDE to run my programs. We will learn how to install Dart SDK in our upcoming Flutter tutorial. Till then, practice on Dartpad Online. Main is the entry point of our program. Without this, our program will not execute. This is how we create variable in Dart. Print is the keyword in Dart to display output on screen. Dart provides multiple ways to declare variables. I am creating another variable age to store number. Now I will print both the values name and age. Here the output comes to an hexagon. Using var, also known as type inference. The var keyword allows Dart to automatically determine the type of the variable based on the assigned value. When I assigned hexagon, Dart infers it as string, and when I assign to it, infers it as integer. Let's print all the variables created using var keyword. Here comes the output. Once Dart infers a type, you cannot change its type. However, you can change its value. It means you cannot assign integer to a variable which is assigned string initially and vice versa. As soon as I assign 10 to name, it throws error. I hope you all got everything till now. Please like, share and subscribe if you like the video. Oh, I forgot to print the variable name again after changing its value. Here comes the output after changing the value of variable name to digital. Now let's see the keyword dynamic. Using dynamic, also known as flexible typing. If you want a variable that can change its type at runtime, use dynamic. Dynamic allows type changes. That is why be careful while using dynamic. It may lead to unexpected error. Here the output comes hello. Here when we change the type of value, it does not throw any error. So the output comes out to be 29. Now we will learn about final and const keyword, also known as immutable variables. That is, their value cannot be changed after they are assigned. Final is variable is assigned a value once, but can be determined at runtime. City is declared a final variable and is assigned a value Noida. As soon as I try to change its value, it throws an error. Now comes the const keyword. Here also we assign a value once, but must be assigned at compile time only. State is const variable and a value Uttar Pradesh is assigned to it. Now if I try to change the value of state, it throws an error. Let's understand the difference between const and final. Final variable need not to be initialized at the time of declaration. But const variable must be initialized at the time of declaration. Otherwise, it throws an error. Let's print both the values. As soon as we change it to const, it throws an error because const variable must be initialized at compile time. I hope you got final and const clearly. Now next is primitive data type in Dart. Dart has 4 primary data types. First one is integer denoted by int, which stores whole number. Our second data type is double, which store decimal numbers. Our third data type is string, which store word or characters. Here in the output, we don't get name instead of Hexagon digital services. So to get exact value, we should use $sign before the variable name. This is called string interpolation. Our fourth data type is Boolean, which stores true or false. Type inference versus explicit typing. Explicit typing is preferred for better readability. Let's quickly recap what we have learned till now. We use var when we don't want to specify the data type ourselves, or we don't know what user will enter and want Dart to infer the type. We use dynamic when data type is to be decided at runtime, such as the value entered by the user, it may be number, string, or Boolean. We use final when we don't want to change its value in future. And final is used when the value may be assigned to it at runtime. We use const when we don't want to change the value, and it must be assigned at the compile time. We use explicit data types when we know what needs to be entered in the variable. Let's understand string in more detail. A string in Dart is a sequence of characters enclosed in single or double quotes. String concatenation is the process of joining two words using plus operator. Let's see this in Dartpad. All the three words got attached without any space, so we have to add space in between them to give better look. This is how a number can be written in string after converting it into string. By the way, string concatenation using plus operator is not a best practice. Instead of that, we use string interpolation coming next. Next method is string interpolation. In this, we use $sign to represent variable in string, otherwise Dart takes it as a normal text. So there are two ways. Let's code them in Dartpad. String name equals to Hexagon. String greeting equals to hello. $name. Let's print this. Here's the output. Let's show how to perform mathematical operation in string using string interpolation. Multi-line strings. We can use either triple single quotes or triple double quotes. Use multi-line strings when working with large text blocks, gesso data, or formatted messages. First method is length. It gives the length of string including space and all characters. Second method is contains. It checks whether a string contains a substring or not. It returns true or false. Third method is split. It is used to split string into a list. Used to break text into parts. Here the string names is separated by comma. fourth method is substring. It is used to extract a part of string from the given string. Index of string starts from 0. The method extract from the index at first parameter to 1 less from the second parameter. Here first parameter is 7 and second parameter is 11, so string extracts from D to T and output comes out to be Dart. Our next topic is numbers and math operations. Dart has two types of numbers. Int used to store whole numbers and double to store decimal numbers. Dart also supports num, which can store both int and double. Next comes arithmetic operators. There are 6 operators: addition, subtraction, multiplication, division, integer division, and modulus. Everyone is aware of first 4 operators, but integer division is same as division operator, but it gives integer part. That is, if result comes out to be 44.25, then output will be 44. Next is modulus operator, which returns the remainder. Next comes type conversion. Sometimes we just need to convert string into integer or double and vice versa. Our first conversion is string to int. Here the variable num st stores 42 as string, and we can convert it into an integer by using int.parse method. Our second conversion is string to double. Here the variable double str stores 3.14 as string, and we will convert it into double by using double.parse method. Be careful while using these conversions, because if the type to which we want to convert the current value stored in the variable is not there, then it will result in a runtime error. To avoid this, we must use try-parse instead of just parse. So the third method is int to string, where we convert integer into a string. So the fourth method is double to string, where we convert double into a string. Let's code what we learned. Our next topic is Dart Math Library. Our first function is sqrt, which gives the square root of a number. For example, sqrt 16 gives 4.0. Our second function is pow, which raises one number to the power of another. For example, pow 2 3 means to raise to the power of 3, which is 8. Our third function is max, which compares to numbers and gives the bigger one. For example, max 5, 10 gives 10. Our fourth function is min, which compares to numbers and gives the smaller one. For example, min 5, 10 gives 5. Our fifth function is sin, which gives the sign of an angle in radians. For example, sin pi 2 gives 1.0. Our sixth function is cos, which gives the cosine of an angle in radians. For example, cos 0 gives 1.0. Our seventh function is random, which generates a random number between 0 and 1. For example, random dot nextable might give something like 0.345. It changes every time. Here the error is because we haven't imported math library. As soon as the library is imported, error is gone. As you can see, when we run our program, again a new number is generated. Our next topic is Boolean and logical operator. In this lesson, we're going to learn about Boolean and logical operators in Dart. These are really important tools that help your programs make decisions. You'll use them to check conditions, filter data, and control how your code runs based on what's true or false. Boolean stores only to values either true or false. Booleans are mostly used with conditions, such as if-else, loops comparisons, etc. In this part, we're talking about comparison operators, also known as relational operators in Dart. These operators are used to compare two values and return a Boolean result, which simply means either true or false. They're super useful when you need to check conditions and control the flow of your code. Here are some common comparison operators. Double equals, written as is equal to, means equal to. For example, A is equal to B checks if both values are the same. In this case, it returns false. Exclamation equals, written as is equal to, means not equal to. So, A is equal to B checks if the values are different. Here, it returns true. The greater than symbol checks if one value is larger than another. For example, A, B returns true. The less than symbol checks if one value is smaller. For instance, A, B returns false. Greater than or equal to, written as is equal to, checks if a value is either greater than or exactly equal to another. For example, A is equal to 10 returns true. And finally, less than or equal to, written as happy smiley, checks if a value is smaller than or equal to another. Like be happy smiley 5, which also returns true. Asterisk asterisk. These operators are simple, but they're really powerful when it comes to making decisions in your programs. Let's code this. Now let's see logical operator. Logical operators are used to combine multiple conditions into a single Boolean expression. There are three types of logical operator: and, or, and not. First, we have and written as two ampersands, like this, and. This operator checks if both conditions are true. For example, if x is true and y is false, then x and y gives us false, because both are not true. Next is the or operator, written as two vertical lines, vertical bar, vertical bar. This means that if at least one condition is true, the result will be true. For example, if x is true and y is false, then x vertical bar, y gives us true, because at least one value is true. Finally, we have the not operator, written as an exclamation mark. This simply reverses the Boolean value. So, if x is true, then x becomes false. These operators are very useful when making decisions in programming. Let's code what we learned. Now the warning is gone as the first condition became false. Let's move to next topic, type checking and typecasting. Type checking is used to verify the data type of a variable at runtime. This helps make sure that you're working with the correct types and helps you avoid unexpected runtime errors. In Dart, we mainly use two operators for type checking: is and is not. These operator checks if a variable belongs to a specific type. If it does, it returns true. For example, if we have a variable and we want to check if it's a string, we can write name is string. If the variable name is actually a string, this will return true. On the other hand, we have the is operator. This is just the opposite of is. It checks if a variable is not of a specific type. So if we write age is string, this will return true if age is not a string. So when do we use these? Type checking is especially useful when you're working with dynamic data or inputs where you're not sure of the type. For example, before doing string operations like .toUpperCase, you can first check if the value is actually a string. This helps prevent errors in your program and keeps your code safe and reliable. Let's code what we just saw. Typecasting is the process of converting one data type into another. This is helpful when you want to safely use specific properties or methods of a certain type. In Dart, we use the as operator for explicit typecasting. This means you're telling Dart to treat an object as a specific type, but only if it actually is that type. For example, if we have a variable that we know is a string, we can write var name is equal to value as string. But here's something important to remember. If the value is not of the type you're trying to cast to, Dart will throw a runtime error. That's why it's always a good idea to check the type first, using the is operator before you cast. This is called safe casting with type checking. It helps keep your code error-free, especially when dealing with dynamic data where the type isn't guaranteed. So remember, always check the type first and then cast to keep your code safe and avoid crashes. Let's code this. Don't worry, in next part, I will be teaching if else. You just focus on that if will only execute if the condition inside if is true. Otherwise, else will execute. Conditions in a program. Conditional statements allow a program to make decisions and execute different blocks of code based on certain conditions. This is essential for controlling the flow of a program. Dart provides several types of conditional statements. If statement. The if statement runs a block of code only if a specific condition is true. If the condition is false, that block is skipped. If-else statement. This is an extended version of if. If the condition is true, one block of code runs. Otherwise, a different block executes. This ensures that something happens regardless of whether the condition is met or not. Else if statement. Sometimes, a program needs to check multiple conditions. Instead of writing multiple if statements, we use else if. This allows us to test different cases one after another and execute the appropriate block when a condition is met. Nested if-else. This is when one if-else statement is placed inside another. It helps when decisions need to be made within another condition, allowing for more complex decision-making. Conditional statements are a fundamental part of programming. They help make programs more dynamic and responsive by allowing different actions based on different conditions. Let's code the same. A switch case statement is used when we need to compare a variable against multiple constant values. Instead of writing multiple if-else conditions, we use switch case to make the code cleaner and more readable. The break statement stops further execution. Once a case matches, the program exits the switch block to prevent unnecessary checks. The default case executes when none of the specified cases match. It acts as a fallback to ensure that some action is taken. The continue statement allows the program to skip the current case and jump to another case. This is useful when multiple cases share the same logic. Switch case is especially helpful when working with fixed values, such as menu options, user input choices, or status codes. It improves code organization and makes it easier to read compared to multiple if-else statements. Let's code what we just learned. The break statement is used to immediately stop execution inside a loop or a switch statement. When break is encountered, the program exits the current loop or case and moves forward with the rest of the code. In a switch statement, break prevents execution from moving to the next case. In a loop, it helps stop iterations when a certain condition is met. In the latest version of Dart, even if you don't use break in a switch statement, the execution does not fall through to the next case. The first matching case runs, and the switch statement exits automatically. Simply put, break is useful when you want to exit early and avoid unnecessary execution. Here we have not used break keyword then, also the execution does not fall through to the next case. The first matching case runs, and the switch statement exits automatically. This is how we use continue statement if we want to skip a case and want to execute multiple cases. Writing an empty case is must for using continue statement, or if we want to skip cases. Default statement is executed when none of the case matches. This was all about switch case and all its keywords break, continue, and default. Let's move to next topic, loops. Loops are a fundamental part of programming, helping us automate repetitive tasks efficiently. Dart provides several types of loops, each serving a specific purpose. First is for loop, runs a block of code a fixed number of times. Second is while loop, runs as long as a condition remains true. Third is do while loop, executes at least once before checking the condition. Fourth is for each loop, iterates over collections like lists and maps. Fifth is break and continue, control the flow inside loops by stopping or skipping iterations. Each of these loops is useful in different scenarios, and we'll explore them in more detail. For loop is used when we know number of iterations. This is the normal way of printing 5 numbers one by one. We can do the same task using for loop and in less number of lines. This is how it works. int I is equal to 0, initializes I with 0. I less than is equal to 5. Loop runs as long as I is less than or equal to 5. I++ increases I by 1 after each iteration. Now comes the while loop. It is used when we don't know the exact number of iterations, but know the condition that determines how long it should run. Do while loop is same as while loop, but the main difference between them is though while loop execute at least once. In this code the condition is false, but the code inside the block is executing at least once. The for each loop is a convenient way to iterate over collections like lists, sets, or maps in Dart. It helps execute a function on each element of the collection without needing a manual index. For example, in a list, for each goes through each item one by one and applies the specified function. In a set, it works the same way, processing each unique element in the collection. When used with a map, for each provides both the key and value, allowing you to work with pairs effortlessly. This makes for each a simple and readable way to handle iteration in Dart. Let's iterate over a list using for each loop. Now let's iterate over a list of string data type. Now let's iterate over a map. I hope you got a short intro of list and map, but don't worry, we will study these in more detail in upcoming part. Let's explore the break and continue statements in loops. The break statement is used to stop the execution of a loop immediately, bringing the control out of the loop. On the other hand, the continue statement is used to skip the current iteration and move to the next one without terminating the loop. Here, I run a loop from 0 to 5 and use an if statement with a condition. If I is equal to 3, the break statement stops the execution of the loop. As a result, when I run the code, it prints only 0, 1, and 2, and then the loop terminates. Now, instead of break, we use the continue keyword. If I is equal to 4, the continue statement skips that iteration and moves to the next one. As a result, when I run the code, it prints 0, 1, 2, 3, and 5, skipping 4, and then the loop completes its execution. And why we use functions? A function is a block of code that performs a specific task. Instead of writing the same code multiple times, we define a function once and call it whenever needed. Why use functions? Reusability, write once, use multiple times. Modularity, breaks large programs into smaller, manageable parts. Readability, makes the code cleaner and easier to understand. A function has a specific structure. First, we define what type of value it will return. Then, we give it a name, and if needed, we provide inputs called parameters. Inside the function, we write the code that performs a task. If required, the function can also return a value. Components of a function. Return type, it tells what kind of value the function will give back. If it doesn't return anything, we mention that too. Function name, this is the name of the function, which we use to call and run it. Parameters, these are optional inputs that we can pass to the function for it to work with. Return statement, this is also optional. It allows the function to send back a result after performing its task. Let's code what we learned so far about function. Here we are defining a function named say hello, whose return type is void, which means it will not return any value. We are printing hello guys in this functions. So whenever we will call this function, it will print hello guys. Here, we call the function twice, and it prints hello, guys 2 times. Instead of writing the same code again, we simply call the function by its name. This is called reusability. We write the function once and use it multiple times whenever needed. Now, we are using a parameter called name, which is of string type. This allows us to print the name along with the message. When calling the function, we must pass a string value as an argument so the function can use it. A function can return a value using the return keyword. To do this, a return type must be specified before the function name instead of using void. This tells what type of value the function will return after execution. Functions are a powerful way to make our code more efficient and reusable. Instead of repeating the same code, we define a function once and call it whenever needed. We can also pass parameters to functions to provide input values, making them more dynamic. If a function needs to return a result, we use the return keyword and specify a return type. However, if a function doesn't return anything, we use void as the return type. By using functions, we can write cleaner, more organized, and easy to manage code. Now, let's dive deeper into function parameters and understand how they make functions more flexible. Function parameters allow us to pass values into a function when calling it. These values are called arguments, and they help us avoid hard-coding values inside a function. Instead, we can pass different values each time we call it, making the function more dynamic and reusable. Types of function parameters in Dart. First, we have required parameters. These are the most common type of parameters, and as the name suggests, they must be provided when calling the function. If we don't pass a value, the code won't work. Second, there are optional positional parameters. These are enclosed in square brackets, meaning they are not mandatory. If we provide them, they must follow the correct order. Otherwise, the function might not behave as expected. Next, we have named parameters, which are written inside curly braces. Instead of passing values in a specific order, we specify the parameter name while calling the function. This makes the code more readable and easier to understand. Named parameters can also be optional, depending on how we define the function. Instead of printing null, we can print customized text. Now, what if we want to use named parameters, but also ensure that the user must provide all the required values when calling the function? To handle this situation, we use the required keyword. This ensures that all specified arguments must be passed. Otherwise, the code will show an error. It helps maintain clarity and prevents missing values when using named parameters. Finally, we have default parameter values. Sometimes, we may want to provide a default value so that even if we don't pass an argument, the function still works properly. This helps prevent errors and ensures the function always has something to work with. By using different types of parameters, we can customize functions to handle a variety of situations, making our code more efficient and flexible. Summary of function parameters in Dart. In Dart, function parameters allow us to pass values when calling a function, making our code more flexible and reusable. Understanding different types of parameters helps us write cleaner and more efficient functions. Required parameters are those that must be provided when calling the function. If they are missing, Dart throws an error because the function expects a value to work with. Sometimes, we may not always need to pass every argument. In such cases, we use optional positional parameters, which are placed inside square brackets. Since they are optional, they might be null, so we use nullable types or provide a default value to avoid issues. However, the order of arguments still matters when passing these parameters. Named parameters, enclosed in curly braces, allow us to specify values using their names instead of relying on position. This makes the function call more readable and easier to understand. Unlike positional parameters, the order doesn't matter when passing named parameters. If a named parameter might be null, we can use the operator to provide a fallback value. By default, named parameters are optional. But what if we want to make sure certain named arguments must be provided? That's where the required keyword comes in. If we mark a named parameter as required, Dart will throw an error if we forget to pass it. This ensures that our function always gets the necessary values to work correctly. To prevent null values, we can set default values for optional parameters. This means that if an argument isn't provided, the function will use the default value instead. This makes function calls more flexible and reliable, as we don't always need to pass every parameter manually. Final recap. Required parameters must be provided or an error occurs. Optional positional parameters allow flexibility, but order matters, and they can be null if no value is given. Named parameters improve readability and allow arguments to be passed in any order. Required named parameters ensure important values are always provided, preventing errors. Default values help avoid null values by providing a fallback option when arguments are missing. By understanding these different types of parameters, we can write efficient, error-free, and more readable Dart functions. Now comes arrow function. Arrow functions provide a shorter and cleaner way to write functions in Dart. Instead of using curly braces and the return keyword, we use the fat arrow to define a function in a more concise way. Now, why should we use arrow functions? First, they make the code shorter and cleaner, reducing unnecessary syntax. Second, they improve readability, making it easier to understand at a glance. And finally, they are perfect for simple one-line functions where we just need to return a value. The syntax is straightforward. Instead of writing a full function with curly braces and a return statement, we simply use the fat arrow to return a value directly. This makes our code more efficient and elegant, especially when working with small functions. Let's have a quick recap of arrow function. Arrow functions help make code shorter and cleaner by replacing curly braces, and the return keyword with a fat arrow is equal to. The syntax is simple. Instead of writing a full function with and return, we use return type function name parameters is equal to expression. Arrow functions are perfect for single-line functions, especially when working with list operations like map and for each. However, they cannot be used for multi-line functions. For that, we need curly braces. Using arrow functions makes code more concise and readable, improving efficiency in Dart. Let's move to next topic, higher order functions. A higher order function is a function that either takes another function as a parameter or returns a function itself. Now, why should we use higher order functions? First, they make code more flexible and reusable, reducing repetition. Second, they are perfect for handling callbacks and functional programming, making code more efficient. And finally, they simplify operations on lists and collections, making tasks like filtering, mapping, and sorting much easier. Higher order functions are a powerful tool for writing clean and efficient Dart code. The function perform operation, INTA, INTB, function operation, is designed to take two numbers and a function as input. Instead of writing separate functions for addition or multiplication, we pass the operation either add or multiply as an argument. This means the function executes dynamically. It doesn't decide what to do on its own. It simply performs whatever operation we pass when calling it. This makes the code more flexible because we can reuse the same function for different calculations instead of writing separate ones for each operation. The multiplier int factor function returns another function that takes a number and multiplies it by the given factor. We can store this return function in variables like double value and triple value, each with a different factor. For example, if we set double value is equal to multiplier 2, calling double value 5 means 5 times 2 equals 10. Similarly, if we set triple value is equal to multiplier 3, calling triple value 4 means 4 times 3 equals 12. This approach allows us to create custom multiplication functions dynamically, making the code more efficient and reusable. So the next topic is anonymous functions, also known as lambda expressions. An anonymous function is a function without a name, typically used for short, one-time operations where defining a full function isn't necessary. Now, why should we use anonymous functions? First, they eliminate the need to create separate functions for simple tasks. Second, they are great for passing functions as arguments, making code more flexible. And finally, they are widely used in list operations like map, filter, and for each, making it easier to manipulate collections. Anonymous functions help write cleaner and more efficient code in Dart. Let's look at the difference between a standard named function and an anonymous function in Dart. First, we have a named function called add, which takes two numbers as input and returns their sum. Since it has a name, we can call it whenever needed. Now, in the main function, we have the same logic written as an anonymous function. But notice something different. It has no name. This function still takes two numbers and returns their sum. But since it's anonymous, it can't be called directly unless we store it in a variable or pass it as an argument to another function. Anonymous functions are great for one-time operations, making code more concise and flexible. Here, we are assigning an anonymous function to a variable called multiply. This function takes two numbers, multiplies them, and returns the result. Since it's stored in a variable, we can use it just like a normal function. When we call multiply 4, 5, it executes the function and returns 4 times 5 equals 20. This method allows us to define functions on the go, making our code more flexible and efficient. We can pass anonymous functions as arguments to other functions, like for each. In this example, we have a list of names, and we want to greet each person individually. Instead of using a loop, we use the forEach method, which goes through each name in the list. Inside forEach, we pass an anonymous function that takes a single name as input and prints hello, name, for each person. When an anonymous function has only one expression, we can simplify it by using arrow syntax is equal to instead of curly braces. This makes the function shorter and more readable while still keeping the same functionality. Arrow functions are perfect for quick operations like calculations, list manipulations, and simple return statements. In Dart, we can explicitly define function types when using anonymous functions. In Dart, functions can be stored in variables, just like numbers or strings. By using function types, we can ensure that the function takes the correct input and returns the expected output. For example, int function, int, means the function must take an integer as input and return an integer as output, preventing type mismatches. And to make the code even shorter and cleaner, we can use arrow syntax is equal to instead of curly braces. This approach makes functions more flexible, reusable, and type-safe. Let's summarize everything we've learned about anonymous functions in Dart. First, anonymous functions are functions without a name. Instead of defining them separately, we write them inline wherever they are needed. The basic syntax for an anonymous function is parameters, function body. This allows us to create small, reusable functions on the spot. Anonymous functions can also be stored in a variable, allowing us to call them later, just like regular functions. Additionally, they can be passed as arguments to other functions, making them extremely useful in functional programming. To make the code even shorter and cleaner, we can use arrow functions is equal to. This is especially helpful when the function consists of just one expression, as it removes the need for curly braces and the return keyword. Lastly, we can define the function type explicitly using function or return type function parameter type. This ensures type safety, making our code more organized and predictable. By using anonymous functions, arrow functions, and function types, we can write efficient, flexible, and readable code in Dart. Our first collection is lists. A list is an ordered collection of items, just like an array in other programming languages. Each item in the list is assigned an index, starting from 0, making it easy to access specific elements. Now, why should we use lists? First, lists allow us to store multiple values in a single variable, instead of creating separate variables for each item. Second, lists maintain the order of elements, meaning the items stay in the sequence in which they were added. And finally, lists come with powerful built-in methods, making it super easy to add, remove, sort, and manipulate data efficiently. Lists in Dart are of two types, based on the kind of data they hold. First, we have the type list. This type of list only holds elements of a specific data type. For example, a list of integers can store only integer values, ensuring type safety. Second, we have the dynamic list. This type of list can hold elements of different data types, meaning we can store integers, strings, booleans, or any other data type in the same list. Let's code what we learned just now. This was typed list having only specific type of elements only. Now let's see dynamic list. We can create an empty list, and then we can add elements later. Now we will see various methods in list. Dart lists come with several built-in properties that help us inspect and work with them efficiently. First, we have length, which tells us the number of elements present in the list. Next, we have isEmpty, which checks if the list is empty. If the list has no elements, it returns true, otherwise, it returns false. Similarly, isNotEmpty does the opposite. It checks if the list is not empty and returns true if it contains elements. Then, we have first and last. The first property returns the first element of the list, while last gives us the last element. Finally, the reversed property allows us to get a reversed version of the list, returning the elements in opposite order. Let's code what we learned just now. There are multiple ways to iterate over a list in Dart, allowing us to access and process each element efficiently. First, we have the for loop. This is the traditional method where we use an index to access each element one by one. It gives us complete control over the iteration process. Next, we have the for in loop. This method simplifies iteration by directly accessing each element without needing an index. It makes the code cleaner and more readable. Finally, we have the for each method. This is a built-in function that allows us to apply a function to every element in the list. It's widely used in functional programming for performing actions on each list item in a more compact way. Let's code the following. Let's quickly go over everything we've learned about lists in Dart. First, lists are ordered collections of items, just like arrays in other programming languages. Each element is stored at a specific index starting from 0. There are two types of lists in Dart. Typed lists allow us to store only a specific data type, while dynamic lists can store different types of values in the same list. To modify a list, we have several built-in methods. We use add to insert an element at the end, remove to delete a specific element, and insert to add an element at a specific index. These methods give us complete control over how we manipulate our lists. Dart also provides helpful properties to inspect lists. Length tells us how many elements are in the list, isEmpty checks if the list has no elements, and first helps us quickly access the first element of the list. Finally, when working with lists, we can iterate over elements using different techniques. The for loop gives us index-based control, the for in loop simplifies iteration by directly accessing elements, and the for each method allows us to apply a function to every item in the list efficiently. Lists are powerful and flexible, making them essential when working with collections of data in Dart. Our next collection is sets. A set is a collection where all elements are unique and unordered. Unlike lists, sets do not maintain the order of elements, and they automatically remove duplicate values. Now, why should we use sets? First, they ensure that all elements are unique, meaning no duplicates are allowed. Second, sets allow us to perform mathematical operations like union, intersection, and difference, making them useful in many programming scenarios. And finally, they help in removing duplicates from a list, making data handling much easier and more efficient. So, whenever you need to store unique values without worrying about order, sets are the perfect choice. In Dart, you can create two types of sets. A typed set, which holds elements of a specific type, ensuring all values belong to the same data type. A dynamic set, which can store elements of different types, making it more flexible when working with mixed data. Whether you need type safety or flexibility, sets in Dart provide both options. Let's see how to add and remove elements in sets. Here's the quick recap of sets. Sets can be of two types. Typed set holds elements of a specific type, ensuring type safety. Dynamic set can hold elements of different data types. Sets are unordered collections of unique elements, meaning they automatically remove duplicates and do not maintain a specific order. This makes them ideal for storing distinct values without worrying about their sequence. To modify a set, you can add, insert a single element, add all, merge multiple elements at once, remove, delete a specific element, clear, remove all elements. Sets support powerful operations such as union combines to sets, set A dot union, set B. Intersection finds common elements, set A dot intersection, set B. Difference retrieves unique elements from one set, set A dot difference, set B. For iterating through a set, you can use a for in loop to access elements one by one. Use for each to apply a function to each element. Since sets automatically remove duplicates, they are perfect for scenarios where you need to eliminate repeated values and work efficiently with unique data. Let's move to next collection in Dart, that is maps. A map is a powerful data structure that stores information in the form of key-value pairs. Think of it like a dictionary, where each key is unique and is linked to a specific value. This makes it incredibly useful when you need to organize and retrieve data efficiently. Why should you use maps? One of the biggest advantages of using maps is that they allow for quick data lookups. Instead of searching through a list or a set, you can access a value instantly just by referring to its key. Maps are also great for storing structured data. For example, if you're building an app, you can use a map to store user profiles, where each key represents a username and the value holds their details. Similarly, they're useful for handling configuration settings, where each key represents a setting name and the value stores its assigned value. Another important feature of maps is their flexibility. Unlike lists or sets, where elements are usually of the same type, maps allow both keys and values to be of any data type. You could have string keys with integer values, integer keys with string values, or even more complex combinations depending on your needs. In short, maps provide a fast, organized, and flexible way to store and access data, making them an essential tool in Dart programming. A map where both keys and values have specific types is known as typed map, such as here, we have keys of string types and values of integer type. A map where both keys and values have different types is known as dynamic map, as shown here. We can create an empty map and add values later. In Dart, maps are a great way to store and manage data using key-value pairs. Instead of accessing values by index, like in lists, maps let you retrieve values using unique keys. Keys must be unique, but values can repeat. Types of maps. There are different types of maps in Dart, depending on how you want to structure your data. First, we have a typed map. This ensures that both the keys and values are of a specific type, making your data more predictable. Then, there's a dynamic map, which allows both keys and values to be of any type, giving you more flexibility. And finally, an empty map, where you start with no data and add values later as needed, adding, updating, and removing entries. Now, let's talk about how we can modify a map. To add a new entry, we can use square brackets. Or if we want to insert multiple key-value pairs at once, we use the add-all method. To update an entry, we can simply reassign a new value using an existing key. But for more control, we can use the update method. If the key doesn't already exist, we can use the ifAbsent parameter to add it automatically. To remove an entry, we use the remove key method to delete a specific key-value pair. And if we want to clear everything, we use clear. Important map properties and methods. Maps also come with some helpful properties to manage and inspect the data. Keys returns all the keys in the map. Values returns all the values. Length gives the total number of key-value pairs. Is empty checks if the map has no entries. Contains key checks if a specific key exists. Contains value checks if a certain value is present. Iterating over a map. Now, how do we loop through a map? One way is by using forEach, which applies a function to each key-value pair. Another way is a foreign loop with entries, which lets us directly access each key-value pair. And if needed, we can also iterate over just the keys or just the values separately. Why use maps? Maps are incredibly fast and efficient, making them perfect for storing structured data, whether it's user profiles, configuration settings, or API responses. If you need a quick and reliable way to organize and retrieve data, maps are the way to go. How to manage errors effectively, prevent crashes, and write more robust code. An exception is an error that happens while a program is running, causing it to stop unexpectedly. In Dart, exceptions are used to indicate that something went wrong during execution. Let's look at some common situations where exceptions can occur. Imagine trying to divide a number by 0. Mathematically, that's undefined, so Dart throws an exception. Another common case is accessing a null object. If we try to use something that doesn't exist, the program crashes. Parsing errors can also cause exceptions. For example, if we try to convert the text ABC into a number, Dart won't be able to process it and will throw an error. And finally, file not found errors. If we try to open a file that doesn't exist, the program won't be able to continue as expected. These are just a few examples. But understanding exceptions is key to writing stable and error-free applications. In this Dart program, we attempt to perform an integer division by 0 using the integer division operator. However, since division by 0 is mathematically undefined, Dart throws an error. To prevent this, we use a try-catch block. The try section contains the risky operation, and if an error occurs, the catch block captures it and prints a custom error message instead of stopping the program abruptly. As a result, instead of crashing, the program gracefully displays an error message. This method ensures that the application continues running smoothly even when unexpected errors occur. Using try-catch is an essential best practice for handling runtime errors in Dart programming. In Dart, the catch block is used to handle errors, and the variable E represents the exception that occurred. When an error happens inside the try block, Dart automatically passes the error details into E. This helps in identifying what went wrong and allows us to print or log the error message for debugging. For example, when we try to divide by 0, Dart throws an error saying unsupported operation, infinity. The catch block captures this error in E, allowing us to display a user-friendly message instead of crashing the program. Using E is important because it gives us insight into the type of error, making it easier to handle different exceptions in different ways. This helps in writing more robust and error-free Dart applications. In this program, we are using a try-catch finally block to handle errors. Since division by 0 is not allowed, an error occurs, and the catch block captures it, displaying an error message. Despite the error, the finally block executes, printing a message that runs no matter what. Next, we modify the program to perform a valid division. This time, since there is no error, the catch block is skipped, and only the result is printed. However, the finally block still runs, proving that it always executes regardless of whether an error occurs. The finally block is useful for tasks like closing files, releasing resources, or executing cleanup operations that must happen no matter what. In this Dart program, we attempt to convert a non-numeric string into an integer using the int.parse method. Since the string does not contain a valid number, Dart throws a format exception. To handle this, we use an onFormat exception block, which specifically catches formatting errors. When this error occurs, it prints a message describing the issue. Additionally, we include a general catch E block to handle any other unexpected errors. However, in this case, since the error is a format exception, the first block executes, displaying the message. Using specific exception handling like onFormat exception is a best practice because it allows us to manage known errors separately while keeping a general catch block for any other exceptions. In this Dart program, we have a list containing 4 numbers. Inside the try block, we attempt to access an index that does not exist in the list. Since the index is out of bounds, Dart throws a range error. To handle this, we use an onRangeError block, which catches the specific error and prints a message indicating that the index is out of range. Additionally, we include a general catch block to handle any other unexpected errors. However, since this is a range error, the specific handler executes first. In this Dart program, we have an empty list and attempt to access the first element using the .first property. Since the list has no elements, Dart throws a state error. To handle this, we use an onStateError block, which specifically catches the error and prints a message indicating that the list is empty. Additionally, we include a general catch block to handle any other unexpected errors. However, since this is a state error, the specific handler runs first. Handling such errors ensures that our program doesn't crash and provides a clear message when an operation is attempted on an empty list. In this Dart program, we have an empty list and attempt to access the first element using the .first property. Since the list has no elements, Dart throws a state error. To handle this, we use a try-catch block. The catch block captures 2 parameters, E, which holds the error message, and stack trace, which provides detailed information about where the error occurred in the code. The stack trace is important because it shows the sequence of function calls that led to the error, the exact file and line number where it happened, and the execution order before failure. This information is essential for debugging, especially in large applications, as it helps pinpoint the source of the issue. By logging stack traces, developers can track and fix errors effectively, making the program more reliable and user-friendly. In this Dart program, we define a variable age with a negative value. Since age cannot be negative, we manually throw an argument error inside the try block when the condition is met. Throwing an error like this helps enforce data validation and prevents invalid values from being processed. When the error is thrown, the catch block captures it and prints an error message. Using throw statements is useful for handling invalid input, enforcing business rules, and ensuring that the program does not continue with incorrect data. This approach makes the program more robust and prevents unexpected issues from occurring later. Let's do a quick recap of what we've learned about exception handling in Dart. First, exceptions help us handle unexpected errors in a controlled way, preventing our program from crashing unexpectedly. Instead of stopping execution, we can catch these errors and respond appropriately. Next, we use try-catch finally to manage errors gracefully. The try block contains the code that might throw an exception, the catch block handles the error, and the finally block ensures that important cleanup tasks like closing files or releasing resources always run whether an error occurs or not. It's always a good practice to catch specific exceptions instead of using a general catch-all block. This allows for fine-grained control and helps us handle different types of errors appropriately. For example, catching a format exception separately from a range error ensures we respond correctly to each issue. We also have the ability to throw custom exceptions using the throw keyword. This is useful when we need to enforce specific rules in our program, such as validating user input or preventing invalid operations. And finally, always remember the finally block. It's essential for cleanup operations like closing database connections, freeing up memory, or logging errors, ensuring our program remains efficient and stable. By implementing these best practices, we can write more robust and error-resilient Dart applications. In this video, we will be studying object-oriented programming. Object-oriented programming, or OOP, is a powerful programming paradigm that revolves around objects. These objects serve as building blocks containing both data, known as properties, and functions called methods that operate on this data. Let's break down the core concepts of OOP. A class acts as a blueprint or template for creating objects. It defines what properties and behaviors an object will have. An object is a real-world instance of a class. Each object has its own unique values for the properties defined in the class. Properties, also known as fields, are variables inside a class that hold data. These define the characteristics of an object, like a person's name or a car's color. Methods are functions within a class that determine the behavior of an object. They allow objects to perform actions like processing data, updating properties, or interacting with other objects. By following OOP principles, we can write code that is well-structured, reusable, and easy to maintain, making development more efficient and scalable. In Dart, a class is a fundamental part of object-oriented programming. It acts as a blueprint for creating objects, defining their properties and behaviors. Let's go through each component of a class in detail. A property, also called a field, is a variable inside a class that holds data. Each object of the class has its own set of properties. The data type of a property defines what kind of value it can store. For example, in a class representing a car, properties could include the car's color, speed, and price. Next, we have the constructor. A constructor is a special method that is automatically called when an object is created. Its main purpose is to initialize the properties of the object. The constructor has the same name as the class and does not return any value. If no constructor is explicitly defined, Dart provides a default constructor. By using constructors, we ensure that objects are set up correctly when they are created. The methods inside a class define what actions an object can perform. Methods are functions that can interact with properties, perform calculations, or modify the object state. For example, in a class for a car, a method named drive could increase the speed, while a method named brake could decrease it. When an object of a class is created, the constructor initializes its properties, and methods allow us to interact with and manipulate the object. This structure helps keep code organized, reusable, and easy to manage. By using classes, we can create real-world models in our programs, making the code more structured and scalable. In this Dart program, we define a car class, which serves as a blueprint for creating car objects. Inside the class, we declare three properties: brand, color, and year. These represent the characteristics of a car. Next, we define a constructor using the this keyword, which initializes these properties when a new object is created. The constructor takes three arguments: brand, color, and year, and assigns them to the respective properties of the object. We also define a method called displayInfo. This method prints the details of a car, displaying the brand, color, and manufacturing year. In the main function, we create two car objects. The first car is a Tesla, red in color, manufactured in 2023. The second car is a BMW, blue in color, manufactured in 2020. After creating these objects, we call the displayInfo method on both, which prints their details to the console. This example demonstrates the power of classes and objects in Dart. By defining a class, we can create multiple objects with different values while keeping the structure organized and reusable. This approach makes the code more scalable and easy to maintain. This keyword in Dart is a powerful tool that refers to the current instance of a class. It plays a crucial role in differentiating between instance variables and constructor parameters, or local variables, when they share the same name. Without it, Dart may not correctly assign values to the instance variables, leading to unexpected behavior. Why do we need this? Let's consider a scenario where we define a class named person with two properties, name and age. To initialize these properties, we pass values through a constructor. However, if the constructor parameters have the same names as the instance variables, a problem arises. For example, in the following class definition, a class named person has two instance variables, name and age. Inside the constructor, we attempt to assign values to these variables using the same parameter names. However, Dart does not automatically recognize which name refers to the instance variable and which refers to the constructor parameter. As a result, the assignment does not work as expected, and the instance variables remain uninitialized or null. This happens because Dart gives priority to the local constructor parameters, treating them as independent variables rather than modifying the instance variables. To solve this, we need a way to explicitly refer to the current instance of the object, and that's where the this keyword comes in. To ensure that the correct values are assigned, we use the this keyword. With this, we explicitly tell Dart that we are referring to the current object's instance variables, not the constructor parameters. For example, in an improved version of our person class, by using this .name is equal to name, we make it clear that the instance variable name should receive the value of the constructor parameter name. The same applies to age. Now, when we create an object like a new person object is created with the name Elise and age 25. Since we correctly assign the values using this, the object now holds Elise as the name and 25 as the age. This ensures that our constructor works as intended, making the code clear, efficient, and bug-free. Let's take an example of a car class, where each car has 3 properties: brand, color, and year. When an object is created, the constructor initializes these values. However, what if we want to change the color of the car after it has been created? How property modification works. First, an object car1 is created with the brand Tesla, color red, and year 2023. The displayInfo method prints the car's details. We then modify the color property of car1 and change it from red to yellow. When displayInfo is called again, it now reflects the updated color yellow. This demonstrates that instance properties can be modified after object creation. Such modifications are useful when we need to update object attributes dynamically during runtime. A constructor is a special method that gets called automatically when an object is created. It helps initialize the object with default values. Now, if you don't define a constructor in a class, Dart automatically provides a default constructor. This means you don't have to manually write one, it's there by default. Let's break down its key features. A default constructor doesn't take any parameters. That means you don't need to pass any values when creating an object. If no constructor is defined in a class, Dart creates one automatically. It ensures the object is initialized properly with default values. Now, when should you use a default constructor? When you simply need to create objects without passing any arguments. When you want Dart to handle initialization automatically, so you don't have to set up values manually. So in short, the default constructor is a simple and efficient way to create objects without extra effort. It ensures that every object starts with an initial state, even if you don't explicitly define how it should be constructed. In this example, we have a class called dog. Inside this class, we have 2 properties, name and age. The name property is set to Bruno by default, and the age is set to 2. Now, we also have a method called bark, which prints a message showing that the dog is barking. Since we haven't defined any constructor in the dog class, Dart automatically provides a default constructor. This means that when we create an object of the dog class using dog mydog is equal to dog, Dart will use the default constructor to initialize the object with its default values. Here, dog is a constructor call that creates a new instance of the dog class. In the main function, we create an instance of the dog class called mydog. Then, we call the bark method using mydog.bark. Since the name property is already set to Bruno, the output will be Bruno is barking. This example shows how a default constructor works in Dart by automatically initializing an object with default values when no custom constructor is defined. In Dart, we have something called named constructors, which give us more flexibility when creating objects. Unlike the default constructor, which Dart provides automatically when no constructor is defined, named constructors allow us to define multiple ways to initialize an object. Now, why do we need named constructors? Well, sometimes we might want to create an object with different initial values based on certain conditions. Named constructors make this possible by allowing us to set up different initialization methods inside the same class. For example, imagine we're working with a class that represents a car. One named constructor could initialize the car with default values, while another named constructor could set values based on an older model. This means we can create objects in different ways while keeping our code clean and organized. The best part about named constructors is that they make our code more readable and structured. Instead of relying on just one constructor, we can have multiple ones, each with a clear purpose. So, in summary, heavy checkmark named constructors allow multiple ways to initialize an object. Heavy checkmark, they help set specific values at the time of object creation. Heavy checkmark, they make our code more organized and easier to understand. By using named constructors, we can write better, more maintainable code while keeping things flexible and efficient. We are using named constructors in Dart to provide an additional way to initialize an object of the rectangle class. The class has two properties, width and height, which represent the dimensions of the rectangle. We define a regular constructor that initializes these properties when values are passed during object creation. However, in some cases, we might need a special type of rectangle, a square, where both width and height are equal. Instead of passing to identical values every time, we can create a named constructor called square. This named constructor takes a single parameter, size, and initializes both width and height to this value. This makes it easier to create square-shaped rectangles without repeating the same value twice. In the main function, we first create an object using the regular constructor, passing separate values for width and height. Then, we create another object using the named constructor square, passing only one value, which sets both width and height equally. Finally, we call the display method to print the dimensions of both rectangles. This code shows how named constructors allow us to create objects in multiple ways, making code more readable and efficient. Alternative approaches. Using the late keyword. If we want to initialize fields inside the constructor body rather than in an initializer list, we can declare them as late. This allows us to delay initialization while still following Dart's null safety rules. Another way to avoid initialization issues is by making the fields nullable using. This way, Dart does not require them to be initialized immediately. Let's talk about parameterized constructors and why they are useful. A parameterized constructor allows you to pass values while creating an object, making it much more flexible compared to a default constructor. Instead of relying on predefined values, you can initialize an object with specific values right at the time of creation. This is particularly helpful when you want different objects to have different properties based on the input provided. Now, let's go over some key features of parameterized constructors. First, they allow you to pass arguments while creating an object. This means that instead of manually assigning values after creating the object, you can set them immediately. Second, they help in initializing instance variables with specific values, ensuring that an object starts with meaningful data. And finally, they provide more control over object creation by making sure the required data is passed when an object is instantiated. So, when should you use a parameterized constructor? You should use it when you need to initialize an object with custom values instead of relying on defaults. It is also useful when different objects should have different initial values, such as when data comes from user input or an external source. And most importantly, a parameterized constructor ensures that all necessary values are provided right at the beginning, preventing the possibility of missing or uninitialized data. Overall, parameterized constructors make object creation more efficient, flexible, and structured, giving you better control over how data is assigned at the time of instantiation. Here's how we typically define a parameterized constructor. We create a constructor that takes parameters and then assigns those values to the instance variables inside the constructor body. This method works fine, but it requires writing extra lines of code to manually assign values. Now, there's a better and more concise way to achieve the same result by using the this keyword in the constructor parameter list. Instead of assigning values inside the constructor, we directly use this.width and this.height in the parameter list itself. This automatically initializes the instance variables, making the code shorter, cleaner, and easier to read. So, while both approaches work, using the this keyword is the preferred method as it eliminates redundancy and improves code efficiency. A factory constructor is a special type of constructor in Dart that provides more control over how objects are created. Unlike a regular constructor, which always creates a new instance of a class, a factory constructor can either return a new object or return an existing instance based on specific conditions. This makes it highly useful in scenarios where object creation needs to be optimized. Now, why do we use a factory constructor? One of the key reasons is to return an existing instance instead of creating a new one every time. This is particularly useful in situations where multiple parts of a program need access to the same object rather than creating duplicates. Another important use case is when we need to perform some logic before creating an object. For example, if we are fetching data from an API or a database, we might want to check if the data is valid before creating an instance. Factory constructors are also widely used for implementing the Singleton pattern, which ensures that only one instance of a class exists throughout the application. This is helpful in cases like managing a database connection or a network service where multiple instances would be inefficient. Additionally, when working with APIs or databases, a factory constructor allows us to control object creation based on external data. If certain conditions aren't met, instead of creating a new instance, we might return a pre-existing one or even throw an error. Now, let's talk about the key features of factory constructors. First, they are declared using the factory keyword, which distinguishes them from normal constructors. Unlike regular constructors, they don't always create a new instance. Instead, they can return an existing object or even an instance of a subclass. They allow us to perform additional logic before object creation, such as validation, caching, or applying conditions before returning an instance. When should you use a factory constructor? When the object creation process is complex and requires conditions. For example, if creating an object depends on fetching and validating data from a database, a factory constructor allows us to handle that efficiently. When you want to control the number of instances, like in a singleton pattern, where only one instance of a class should exist. When working with APIs or databases, where object creation might depend on whether data is available or not. Instead of creating unnecessary instances, we can return an existing one or handle errors properly. So, in summary, factory constructors provide more flexibility and efficiency in object creation, making them a powerful tool in Dart for managing resources, optimizing performance, and ensuring better control over how instances of a class are created and managed. In this code, the circle class has a private constructor and a factory constructor to control object creation. The private constructor ensures that instances cannot be created directly from outside the class. Instead, the factory constructor handles object creation with additional validation. Inside the factory constructor, we check if the radius is less than or equal to 0. If it is, an error is thrown, preventing the creation of an invalid object. If the radius is valid, the factory constructor calls the private constructor to create an instance. In the main function, we try to create two objects, one with a valid radius 5 and another with an invalid radius -3. The first object is created successfully and its area is printed. The second attempt triggers an error, which is caught and displayed. This approach ensures that only valid circle objects are created while preventing direct access to the constructor. Let's talk about the singleton pattern in Dart. A singleton is a design pattern that ensures only one instance of a class is created and used throughout the application. Now, why is this useful? Well, in many cases, we need a single shared instance instead of creating multiple objects. Some common examples include database connections, logging services, or configuration managers, things that should have a single, consistent instance across the app. Why should we use a singleton? First, it ensures that only one instance of a class exists at a time. That means instead of creating multiple objects, the same instance is reused whenever needed. Second, it helps in saving memory because we're not creating unnecessary duplicate objects. Instead, we just access the existing instance, which improves efficiency. And third, it's useful for maintaining a global state throughout the application. If you need a centralized resource that should remain the same across different parts of your code, a singleton is the perfect choice. How to implement a singleton in Dart? There are two common ways to implement a singleton in Dart. Using a private constructor. The first approach is by using a private constructor. This works by declaring a static instance of the class inside itself. The constructor is private, which means objects cannot be created directly from outside the class. We provide a static method or getter that allows access to the single instance. This ensures that whenever we try to get an instance of the class, we always get the same one. Using a factory constructor. Another way to implement a singleton is by using a factory constructor. We still declare a static instance inside the class. Instead of a normal constructor, we use a factory constructor that returns the same instance every time. If an instance doesn't exist, it creates one. Otherwise, it simply returns the existing instance. This method ensures that only one object of the class is ever created. Both of these approaches help in controlling object creation, and make sure that there is only one instance of the class being used throughout the application. When should you use a singleton? A singleton is useful when you need a single shared resource that should not have multiple instances. For example, when working with a database connection, a singleton ensures that only one connection is maintained throughout the application rather than opening multiple connections unnecessarily. Another common use case is managing global state, such as app configurations or authentication. Having a singleton for these ensures that the same data is accessed consistently across the application without needing to pass it around manually. A singleton is also helpful when you need to ensure consistent access to a resource without creating redundant instances. This prevents unnecessary memory usage and keeps the application more efficient. In short, the singleton pattern provides a single point of access to an object, ensuring that only one instance exists and is shared efficiently across the application. Alright, let's start by creating a singleton class in Dart. First, we'll define a class called logger. Inside this class, we need to make sure that only one instance of this class can ever exist throughout the application. To do this, we'll create a private constructor. A private constructor is defined by adding an underscore before its name like this. This prevents the class from being instantiated from outside. Next, we need a static instance of the logger class. This will hold the only instance of our singleton. Since it's static, it belongs to the class itself and not to any particular object. Now, to ensure that every time we try to create a logger object, we get the same instance, we use a factory constructor. The factory constructor checks if the instance already exists. If it does, it simply returns the existing instance. Otherwise, it initializes it for the first time. Let's also add a simple log method inside our class that will print messages. This will simulate how logging works in real-world applications. Now moving on to the main function, we'll create two objects of logger. But because of our singleton implementation, these two objects should actually be the same instance. Let's log a message using one of them. And finally, to verify that both logger1 and logger to refer to the same object, we'll use the identical function. If our singleton is working correctly, it should return true, indicating that both variables hold the same instance of the logger class. Now let's check the output. The first line will print the log message as log hello world, and the second line will return true, confirming that both objects are indeed the same instance. And that's it. We've successfully implemented a singleton in Dart using a private constructor and a factory constructor. Now, no matter how many times we try to create an object of this class, it will always return the same instance. We will explore the concept of encapsulation, understand its importance, and learn how it helps in structuring secure and well-managed code. Encapsulation is a fundamental concept in object-oriented programming that helps in protecting the internal details of a class. Instead of allowing direct access to variables, we restrict it and provide controlled ways to read or modify data. Now, why do we use encapsulation? First, it protects data from unwanted changes. Imagine if any part of the program could directly modify an object's properties. This could lead to unexpected behavior or even errors. Encapsulation prevents this by restricting direct access. Second, it allows controlled access to fields. Instead of exposing variables, we provide methods to access or update them. This ensures that data is always handled in a safe and structured way. Third, it helps in maintaining data integrity. Since we can control how data is accessed or modified, we can apply validation rules before making any changes. This helps prevent invalid data from being stored inside an object. In Dart, we achieve encapsulation by using private variables and getters and setters. A private variable is simply a variable that starts with an underscore, which makes it inaccessible from outside the class. But since we may still need to access or modify it, we use getter methods to retrieve the value and setter methods to update it with proper validation. So, in short, encapsulation ensures better security, control, and reliability of our code by restricting direct access to data while still allowing necessary modifications through controlled methods. Here, we have a class called person. Inside this class, we define two variables. First, we have name, which is a public variable, meaning it can be accessed from anywhere. Then, we have underscore-age, which is a private variable, meaning it can only be accessed within this class. Now, to display these values, we create a method called display, which prints both the name and underscore-age values. Moving on to the main function, we create an object person from the person class. Since name is public, we can access and print it without any issue. But when we try to print underscore-age directly from outside the class, we get an error because private variables cannot be accessed outside their class. However, when we call the display method, it successfully prints underscore-age because private variables are accessible within the class itself. Alright, let's break this down step by step and understand how encapsulation works in Dart through this bank account example. We have a class called bank account, and inside this class, we declare a private variable underscore balance, which is used to store the account balance. The underscore before balance makes it private, meaning it cannot be accessed directly from outside the class. Now, since the balance is private, we need a way to access and modify it safely. This is where getters and setters come into play. First, we have a getter method called balance. This allows us to read the current balance of the account without modifying it. Then, we have a setter named deposit, which allows us to add money to the account. But notice the condition inside the setter. If the deposit amount is greater than 0, it adds the amount to the balance. Otherwise, it prints invalid deposit amount, preventing negative deposits. Next, we have a withdraw method that allows money to be withdrawn. Before deducting the amount, it checks if the account has sufficient balance. If the balance is enough, the withdrawal is successful. Otherwise, it prints insufficient balance to prevent overdrawing. Now, let's see what happens in the main function. We create an object called myAccount from the bank account class. Using the setter, we deposit 1000 into the account. We print the balance, which now shows 1000. Then, we withdraw 300, which reduces the balance to 700. Finally, we try depositing a negative amount, minus 500. But since our setter checks for negative values, it prevents this transaction and displays invalid deposit amount. Now, let's look at the output of this program. Current balance, 1000. Balance after withdrawal, 700. Invalid deposit amount. So, what did we learn? Encapsulation ensures that underscore balance is protected and cannot be accessed directly. Getters allow safe access to private data. Setters help control modifications, ensuring only valid data is entered. Encapsulation improves security by preventing unauthorized changes to important variables. And that's how encapsulation and data security work in Dart. Let's understand how encapsulation works in this temperature class. The class temperature has a private variable _Celsius, which is used to store temperature in Celsius. Since it is private, it cannot be accessed directly from outside the class. To manage this, getters and setters are used. There's a getter and setter for Celsius. The getter returns the current Celsius value, while the setter allows modifying it. Similarly, there's a getter and setter for Fahrenheit. The getter converts the Celsius value to Fahrenheit using a formula, and the setter takes a Fahrenheit value, converts it to Celsius, and updates _Celsius. In the main function, an object temp is created from the temperature class. The Celsius setter is used to set the temperature to 25 degrees. When printed, it shows 25 degrees Celsius and 77 degrees Fahrenheit. Next, the Fahrenheit setter is used to set the temperature to 98.6 degrees Fahrenheit. Since the setter converts it to Celsius, the updated Celsius value is printed as 37 degrees. Let's do a quick recap of what we've learned about encapsulation. Encapsulation is all about protecting data and allowing controlled access to it. Instead of exposing variables directly, we use private variables by adding an underscore before their names. This ensures that data cannot be modified accidentally from outside the class. To access private data safely, we use getters and setters. Getters allow us to read the value of a variable, while setters let us modify it in a controlled way. One of the key benefits of using getters and setters is that we can add logic to them. For example, we can validate data before updating a value or format it before returning it. We can also create read-only properties by defining only a getter, meaning the value can be accessed but not modified. Similarly, write-only properties can be created using just a setter, allowing updates but preventing direct access to the value. And if a variable is not initialized immediately but will be assigned a value later, we can use the late keyword to handle it properly. So, encapsulation helps in data security, better control, and maintaining a structured way of accessing and modifying data in Dart. Understand inheritance in object-oriented programming. Inheritance is one of the core principles of object-oriented programming, and it allows a class, known as the child class or subclass, to inherit properties and behaviors from another class, known as the parent class or superclass. This means that the child class automatically gets access to the attributes, that is, variables, and functions defined in the parent class without needing to rewrite them. Let's understand inheritance with a real-life example. Imagine a father and son relationship. The father has certain characteristics like a last name, family values, and wealth. He also has some abilities like working to earn money and guiding the family in important matters. Now, the son is born into the same family. Since he is part of the family, he automatically inherits the last name, the family wealth, and the values from his father. He also learns how to work and guide the family from his father. However, the son may develop his own unique characteristics. Perhaps he is good at playing sports, which is something his father never did. How this relates to programming. In programming terms, the father is the parent class, that is, superclass, which contains common properties and methods that can be used by its children. The son is the child class, that is, subclass, which automatically gets all the properties and behaviors of the parent, but can also introduce new ones or modify existing ones. Benefits of inheritance. Code reusability. Instead of defining common properties and methods in every class, we define them once in a parent class and reuse them in child classes. This reduces redundancy. Hierarchy and organization. It helps establish logical relationships between classes. Just like in a real family, where traits pass from one generation to another, inheritance allows us to build a structured system in our code. Method overriding, that is, customization. A child class can modify or override the methods of a parent class to change its behavior. For example, if the father's method of working is different from the son can redefine the work method in his own way. A quick example in simple terms. If we create a class called father with a method work, and then create a class son that inherits from father, the son will automatically have access to the work method. However, if the son wants to have a different working style, he can override the work method and define it in his own way. This is how inheritance makes programming more efficient, organized, and easier to maintain. Let's understand this concept step by step. In this example, we have two classes, animal and dog. The animal class is the superclass, which means it serves as the base or parent class. It has a general behavior, which is making a sound. Then, we create a dog class, which is a subclass of animal. This means the dog class inherits all the properties and behaviors of the animal class. However, the dog class also has its own unique behavior, barking. To establish this relationship, we use the extends keyword. This tells Dart that the dog class is inheriting from the animal class. Now, when we create an object of the dog class, it automatically has access to the method from the animal class, even though it was not explicitly defined inside the dog class. Along with that, the dog class can have its own additional methods. When we run the program, the dog object is able to perform both actions, making a general animal sound inherited from the superclass and barking, which is specific to the dog class. This is the power of inheritance. It helps us avoid repeating code and allows us to define shared behaviors in a parent class while letting child classes extend or customize that behavior as needed. This code demonstrates inheritance in Dart. The animal class serves as the superclass with a property name and a method speak. The dog class extends animal, inheriting its properties and methods while also introducing a new property breed. In the dog class, the super keyword is used to pass the name parameter to the animal constructor. The display method prints the dog's name and breed. In main, an object of dog is created with the name Goldie and breed Golden Retriever. The object calls speak, which it inherits from animal, and display, which is unique to dog. Let's now understand method overriding in object-oriented programming. Method overriding allows a subclass to provide its own specific implementation of a method that is already defined in its superclass. When the method is called on an instance of the subclass, the overridden version is executed instead of the original one. Key features of method overriding. First, the method in the subclass must have the same name, return type, and parameters as the one in the superclass. Second, we use the @override annotation to explicitly indicate that a method is being overridden. Though it's optional, it improves code readability and ensures that we are correctly overriding a method. Finally, method overriding allows us to customize the behavior of inherited methods, making the subclass more specific and functional. Why use method overriding? Method overriding is essential when we want a subclass to behave differently while keeping the same method structure. It supports polymorphism, meaning that the correct method is executed based on the object type at runtime. And lastly, it makes the code more flexible and reusable by allowing modification of specific parts of an inherited method rather than rewriting the entire class. This is how method overriding helps in writing efficient and structured code in object-oriented programming. Let's understand this code and how the super keyword works in Dart. We have a superclass called animal, which has a variable named name and a method called makeSound. The makeSound method prints a generic message that animals make different sounds. Next, we have a subclass called dog, which extends the animal class. In the constructor of dog, we use super.name to modify the value of the name variable inherited from the superclass. This means whenever we create a dog object, it automatically updates the name property to dog. Inside the displayInfo method, we use super.name to access the inherited variable from animal and we print it. We also print the breed of the dog, which is a property specific to the dog class. Finally, we use super.makeSound to call the makeSound method from the animal class, which prints the message animals make different sounds. In the main function, we create an object of dog, passing the breed golden retriever. Then we call displayInfo, which prints the animal type, breed, and the inherited sound message. So, in summary, the super keyword allows the subclass to access and modify inherited properties and call methods from the superclass. In this example, we are demonstrating method overriding in inheritance, specifically how we can override getter and setter methods in a subclass. We start with the employee class, which has a private salary variable. To enforce encapsulation, it provides a getter for bonus, which calculates 10% of the salary, and a setter for salary, which ensures the salary cannot be set to a negative value. Now, we create the manager class, which extends employee and overrides both the getter and setter. The bonus getter is overridden to return 20% of the salary instead of 10%. As managers receive higher bonuses, the salary setter is also overridden. Unlike regular employees, a manager's salary must be at least 5,000. If a lower value is assigned, an error message is displayed. Instead of updating the salary finally, in the main function we create an employee and a manager object. We print their respective bonuses. We update the employee salary. Using the setter, we try to set an invalid salary for the manager, which triggers an error message due to the overridden setter. One important fix in this code is that we should not access the salary variable directly in main because it is private. Instead, we should use a getter for salary. This ensures proper encapsulation and follows best practices in Dart. In this quick recap, let's go over the key concepts of inheritance in Dart in detail. First, we have the extends keyword. This is used when we want a class to inherit the properties and methods of another class. The class being inherited from is called the superclass, and the class that is inheriting is called the subclass. This allows us to reuse code efficiently instead of writing the same methods and properties again in every class. By extending a class, the subclass automatically gains access to all the non-private properties and methods of the parent class. Next, we have the @override annotation. This is used when we want to change the implementation of a method that we inherited from the superclass. While this annotation is not required, it improves code readability and ensures that we are correctly overriding a method. If the method signature does not match the original method in the parent class, the compiler will generate an error, preventing mistakes. Overriding allows subclass to provide their own custom behavior while still maintaining the same method structure. Now, let's talk about the super keyword. This keyword is essential when working with inheritance because it allows a subclass to directly access properties and methods of the superclass. For example, if the parent class has a method that we still want to use but also want to add something extra to it, we can call super.methodName inside the subclass method before or after adding our custom behavior. Similarly, the super constructor can be used to pass values to the parent class when creating an object of the subclass. Finally, we also have the concept of inheriting and overriding getters and setters. Getters and setters allow controlled access to private properties. When a subclass overrides a getter, it can modify the way data is retrieved. Similarly, overriding a setter allows us to add additional validation or conditions before modifying a value. This is useful when different classes need different rules for handling data, while still using the same method names for consistency. By understanding and implementing these concepts, we can write more flexible, organized, and reusable code using inheritance in Dart. In this tutorial, we explore polymorphism in object-oriented programming and understand how it enhances code flexibility and reusability. Polymorphism is a fundamental concept in object-oriented programming that allows a single method to take multiple forms. The word polymorphism itself means many forms, and in programming, it refers to the ability of a subclass to define a method with the same name as in its superclass, but with a different implementation. This means that the same method can behave differently depending on the object that calls it. Now, why do we use polymorphism? First, it promotes code reusability by allowing us to write a single method in the superclass and reuse it in multiple subclasses without rewriting the logic. Second, it enhances extensibility, meaning we can easily introduce new behaviors in subclass without altering the existing code in the superclass. And third, it increases flexibility as it allows us to achieve dynamic behavior at runtime where the appropriate method is executed based on the object type. By using polymorphism, we can write cleaner, more maintainable, and scalable code, making our programs more efficient and adaptable to change. This code demonstrates polymorphism through method overriding. In polymorphism, a subclass can provide a different implementation for a method that exists in its superclass while keeping the method name the same. This allows objects of different classes to respond to the same method call in different ways. The parent class has a method named methodName that provides a base implementation. The child class inherits from parent using the extends keyword and overrides the method name to provide a different implementation. When we call method name on an object of the child class, it will execute the overridden version instead of the one from the parent class. This allows us to treat different objects in a consistent way while still allowing them to have unique behaviors. Polymorphism makes code more flexible and reusable, as we can call the same method on different objects without worrying about their specific class implementations. This code demonstrates polymorphism through method overriding. The animal class has a makeSound method that is inherited by its subclass dog and cat. Each subclass overrides this method to provide its own specific implementation. The dog class overrides makeSound to print dog barks. The cat class overrides makeSound to print cat meows. In the main function, calling makeSound on different objects results in different outputs based on the object type. This shows polymorphism, where the same method behaves differently depending on the object that calls it, making the code more flexible and reusable. In this example, we are demonstrating runtime polymorphism in Dart. Instead of creating separate objects for dog and cat, we use a single reference variable of type animal. First, myAnimal is assigned an animal object, so it calls the makeSound method from the animal class. Then, myAnimal is assigned a dog object. Since dog overrides makeSound, it now calls the dog's version of the method. Finally, myAnimal is assigned a cat object, and it calls the makeSound method from the cat class. This is called runtime polymorphism because the method that gets executed is determined at runtime based on the actual object assigned to myAnimal. Even though myAnimal is declared as an animal, it dynamically adapts to dog and cat at runtime, executing the correct overridden method. This approach makes the code more flexible since we can assign different objects to the same reference variable. It also improves extensibility as new subclass can be added without modifying the existing logic. By using a single reference instead of multiple object variables, we also ensure efficient memory usage. Runtime polymorphism is a powerful feature in object-oriented programming that makes code more scalable, maintainable, and reusable. In this example, we're using polymorphism to simulate different types of payments. We start with a base class called payment, which has a method named processPayment. This method takes an amount and simply prints a generic payment message. Now we have three subclasses: credit card payment, PayPal payment, and Bitcoin payment. Each of these classes overrides the processPayment method to provide its own specific implementation. In the main function, we declare a variable payment of type payment. Here's where polymorphism comes into play. We first assign it to a credit card payment object. When we call processPayment, it executes the overridden method from the credit card payment class. Then, we reassign the same variable to a PayPal payment object. Again, the method that gets executed is the one inside the PayPal payment class. Finally, we assign it to a Bitcoin payment object. And as expected, it runs the processPayment method defined in the Bitcoin payment class. Even though we're using a single payment reference, it adapts to different object types at runtime and executes the right method each time. This is a perfect example of runtime polymorphism, where the behavior of the method is determined by the actual object assigned at runtime, not just the reference type. This makes the code more flexible, extensible, and easier to maintain as we can add new payment methods without changing the core logic. Let's do a quick recap. Polymorphism is one of the core principles of object-oriented programming, allowing the same method name to perform different behaviors in different classes. Method overriding enables a subclass to provide its own specific implementation of a method that is already defined in the superclass. This allows us to customize inherited behavior without changing the parent class. The @override annotation ensures that a method in the subclass correctly overrides a method from the parent class. While it's optional, it helps improve code readability and prevents accidental mistakes. Dynamic method dispatch, also known as runtime polymorphism, allows method calls to be resolved at runtime. This means that when a parent class reference holds a subclass object, the overridden method in the subclass gets executed instead of the one in the parent class. One of the key advantages of polymorphism is that a parent class reference can be used to store objects of different child classes. This makes our code more flexible and scalable as new subclass can be introduced without modifying existing logic. Real-world applications of polymorphism can be seen everywhere. In payment systems, different payment methods like credit card, PayPal, or Bitcoin can be processed using the same method. In logging frameworks, different logging mechanisms like console logs, file logs, or database logs can be handled using a common interface. And in UI frameworks, different types of buttons, sliders, or form elements can respond uniquely while sharing the same method names. Polymorphism enhances code reusability, improves maintainability, and makes programs more adaptable to future changes. Mastering this concept is crucial for writing efficient and scalable object-oriented applications, understanding their role in creating structured and reusable code. An abstract class serves as a blueprint for other classes. It provides a structured foundation, ensuring that certain functionalities are implemented by its subclass. Unlike regular classes, an abstract class cannot be instantiated directly. This means you cannot create an object from it. Instead, it acts as a base class that other classes must extend and build upon. Now, let's look at some key features of abstract classes. First, an abstract class is declared using the abstract keyword. This tells Dart that the class is incomplete and must be extended by another class before it can be used. Second, an abstract class can contain both abstract methods and concrete methods. Abstract methods are declared without a body. This means they don't have an implementation in the abstract class itself and must be overridden in the subclass. Concrete methods, on the other hand, are fully implemented methods that subclass can inherit and use without modification. Finally, abstract classes promote code reusability and structure. They allow developers to define a common interface for multiple subclasses while still permitting each subclass to implement specific behaviors in its own way. Why should we use abstract classes? First, abstract classes enforce a contract. They ensure that all subclasses implement essential methods, maintaining consistency in design. This is especially useful when working in large teams where uniformity is key. Second, they improve maintainability. By defining shared behaviors in one place, abstract classes keep the code organized and structured. Instead of rewriting the same methods in multiple classes, you can define them once in the abstract class and reuse them in all subclasses. Third, abstract classes support partial implementation. This means you can provide predefined functionality for some methods while leaving others as abstract, requiring subclass to provide their own unique implementations. This balance of flexibility and structure makes your code more scalable and easier to manage. Abstract classes are particularly useful in large applications where multiple related classes need to share common behaviors while still allowing customization for specific needs. They provide a strong foundation for building a well-structured and flexible codebase. An abstract method is a method declared inside an abstract class without a body. It acts as a placeholder that must be overridden by any subclass that extends the abstract class. Since it has no implementation, it enforces a contract, ensuring that all subclasses provide their own version of the method. On the other hand, a concrete method is a fully implemented method inside an abstract class. Unlike an abstract method, it has a body and provides a specific functionality that can be inherited and used directly by subclass without modification. By using abstract methods, we ensure that subclass define their own unique behaviors, while concrete methods allow code reuse, improving maintainability and reducing redundancy. This code is a perfect example of how abstract classes and abstract methods work in Dart. The shape class is declared as abstract, meaning it serves as a blueprint for other classes, but cannot be instantiated directly. It contains an abstract method draw, which has no body. This method must be overridden by any subclass that extends shape. A concrete method displayInfo, which has a body and provides a common implementation that can be used directly by subclass. The circle and rectangle classes inherit from shape and provide their own custom implementation of the draw method using method overriding. In the main function, we create instances of circle and rectangle. Each object calls draw, which executes its overridden version of the method. Both objects, also called displayInfo, which runs the inherited method from the shape class. Key takeaways: abstract classes define a common structure for multiple subclass. Abstract methods must be overridden in the subclass. Concrete methods provide shared functionality. Reducing code duplication. Polymorphism allows us to treat different shapes uniformly while enabling each to have unique behavior. This approach ensures code consistency, reusability, and flexibility, making it easier to manage complex applications with multiple related classes. In Dart, an interface defines a contract, a set of methods that any class must implement if it chooses to follow the interface. This approach helps achieve abstraction, enforce specific behaviors, and promote code reusability in your application. Implementing an interface in Dart. To implement an interface in Dart, we use the implements keyword. When a class implements an interface, it must override all methods defined in that interface. This ensures that every implementing class provides its own custom logic while still following the defined structure. Unlike inheritance, where a subclass can inherit method implementations from a parent class, implementing an interface only enforces the structure, requiring the class to define its own implementations for each method. By using interfaces, you can design flexible, scalable, and modular applications, ensuring a clear and consistent code structure. Interfaces in Dart provide several important benefits that help in writing structured and efficient code. The first benefit is consistency. Interfaces ensure that multiple classes follow a common structure. This means that any class implementing an interface must include all the required methods, making the code more organized and predictable. The second benefit is flexibility. In Dart, a class can implement multiple interfaces, unlike inheritance, where a class can extend only one parent class. This allows different behaviors to be combined in a single class, improving code organization and making it easier to adapt to different requirements. The third benefit is code reusability. Interfaces promote a modular approach to development, making the code easier to maintain and extend. When a project grows, having well-defined interfaces helps in updating or modifying functionality without affecting other parts of the code. By using interfaces, a structured yet flexible architecture is achieved, ensuring that the code remains scalable and easy to manage. In this example, printable is an interface that defines a printertails method but doesn't provide any implementation. The book and magazine classes implement this interface, meaning they must provide their own version of printertails. Unlike abstract classes, interfaces only declare methods, ensuring that each class implements them in its own way. This makes the code more flexible and reusable. By using polymorphism, we can store both book and magazine objects in a printable reference. This allows different types of objects to be handled in a uniform way, making the code more organized and easier to expand in the future. In this code, we are demonstrating the concept of multiple interfaces using the readable and writable interfaces. The readable interface has a read method and the writable interface has a write method. Both methods are declared but not implemented. The document class implements both readable and writable, meaning it must provide its own implementation for the read and write methods. This allows document to inherit behaviors from multiple sources, making it more versatile. In the main function, we create an instance of document and call both methods. This shows how a single class can inherit and implement multiple behaviors using interfaces, ensuring flexibility and better code organization. Let's see a real-world example of how interfaces and polymorphism work in a payment system. Here, we have an abstract class payment that acts as a blueprint. It defines a method process payment, but it doesn't provide any implementation. This ensures that any class implementing payment must define its own way of processing payments. The credit card payment and PayPal payment classes implement the payment interface and provide their own logic. When a credit card payment is processed, it prints processing via credit card. And when PayPal is used, it prints processing via PayPal. In the main function, we store different payment methods in a list of payment objects and use a loop to call process payment. Thanks to polymorphism, the correct method is executed based on the actual object type at runtime. This approach makes the code flexible and scalable. New payment methods like Bitcoin or UPI can be added just by implementing payment without changing existing logic. This is the true power of interfaces and polymorphism in object-oriented programming. Let's break down the key differences between abstract classes and interfaces in Dart. First, keyword usage. An abstract class is declared using the abstract keyword, while an interface is implemented using the implements keyword. Next, instantiation. Neither abstract classes nor interfaces can be instantiated directly. Instead, they must be extended or implemented by another class. Now, let's talk about methods. Abstract classes can have both abstract methods, which don't have a body, and concrete methods, which are fully implemented. On the other hand, interfaces can only contain method declarations, meaning all methods must be overridden in the implementing class. Moving on to multiple inheritance. Abstract classes only support single inheritance, meaning a class can extend only one abstract class. However, interfaces support multiple implementations, allowing a class to implement multiple interfaces at once. Finally, the use case. Use abstract classes when you want to provide a common base with shared logic while ensuring certain methods are implemented in subclass. Use interfaces when you want to define a structure or contract that multiple unrelated classes must follow without enforcing shared functionality. In summary, abstract classes help in code reusability with some predefined behavior, while interfaces help in defining a set of rules that classes must adhere to. Understanding the difference between the two is essential for designing efficient and scalable applications, and how they help in reusing code efficiently without relying on traditional inheritance. A mixin is a way to reuse code in multiple classes without using inheritance. Instead of creating deep inheritance trees, Dart allows classes to mix in additional functionality using the with keyword. This makes the code more modular and flexible. Why use mixins? Avoids complex inheritance. Instead of making long chains of parent and child classes, mixins allow us to add specific behaviors to multiple classes easily. Promotes code reusability. The same mixin can be used in different classes without writing duplicate code. More flexibility. A class can use multiple mixins, allowing us to combine functionalities as needed. How to use mixins? Use the mixin keyword to define a mixin. Apply the mixin to a class using the with keyword. Mixins cannot be instantiated on their own. They are only meant to provide additional methods and properties to other classes. By using mixins, we can keep our code clean, maintainable, and reusable. They're a powerful feature in Dart that helps in writing efficient and scalable programs. Let's write the code to understand the mixin better. Let's understand mixins in Dart with this example. We have two mixins, flyable and singable, each providing a specific behavior. The flyable mixin has a fly method that prints flying high in the sky. The singable mixin has a sing method that prints singing a beautiful song. Then we have a bird class that uses both flyable and singable mixins with the with keyword. This means the bird class inherits the fly method from flyable and the sing method from singable without needing traditional inheritance. Inside the main function, we create an object of bird. The bird first calls its own display method, which prints I am a bird. Then it calls fly from the flyable mixin and sing from the singable mixin, demonstrating how mixins add functionalities to a class. Mixins provide a flexible way to add reusable behaviors to multiple classes without deep inheritance, making the code more modular and maintainable. Mixins and inheritance both provide code reuse but serve different purposes. So the first difference is keyword. Mixins use mixin and are applied with keyword. Inheritance extends to inherit from a base class. The second difference is code reuse. Mixins add extra functionality without modifying the class hierarchy. Inheritance allows a class to inherit properties and methods from a single parent. The third difference is multiple sources. Mixins allow a class to inherit behaviors from multiple mixins. Inheritance follows a single inheritance model, meaning a class can only extend one parent. The fourth difference is use case. Mixins are used when multiple classes need shared behavior without being related. Inheritance is used when a class has an is-a relationship with another class. Alright, let's break down this code step by step. Here, we have three mixins: flyable, invisible, and strong. Each of these mixins defines a specific ability that can be added to a class. Flyable provides a method called fly, which prints flying like a superhero when called. Invisible provides a method called turn invisible, which prints now you see me, now you don't. This simulates a superhero turning invisible. Strong provides a method called lift heavy, which prints lifting a car with one hand, representing super strength. Now, we have a class called superhero, which uses all three mixins. The with keyword is used to add multiple mixins, meaning that the superhero class now has all the abilities provided by flyable, invisible, and strong. Inside the superhero class, we also have a name property, which is initialized using a constructor. So, by using mixins, we can add multiple abilities to the superhero class without the limitations of single inheritance. This makes our code more flexible and reusable. Let's understand how the on keyword works in Mixins. First, we have a class vehicle. It has a method move that prints moving on the road. This represents a basic vehicle's movement. Next, we define a mixin called electric. But instead of a normal mixin, we use the on vehicle keyword. This means the electric mixin can only be used by a class that extends vehicle. Inside this mixin, we have a method charge battery that prints charging battery. This represents the functionality of an electric vehicle. Now, we create a class electric car that extends vehicle and also mixes in electric. Because the on keyword restricts the mixin, the class must extend vehicle before it can use electric. In the main function, we create an instance of electric car called Tesla. When we call Tesla.move, it prints moving on the road. From the vehicle class, when we call Tesla.chargeBattery, it prints charging battery. From the electric mixin, the on keyword helps keep the code structured and prevents mixins from being used with unrelated classes. This ensures that only vehicles can have electric functionalities. It improves code safety and organization. Alright, let's talk about the static keyword in Dart. Now, whenever we use the static keyword, we're basically saying, hey Dart, this variable or method doesn't belong to just one object. It belongs to the class itself. That means static members are shared across all the objects of that class. No matter how many objects you create, there's only one copy of the static variable or method. Let's understand this better. Imagine you have a class called student, and you want to keep track of how many students have been created. If you use a static variable for that, every time a new object is made, that one shared variable gets updated. Not one per student, just one for the whole class. Now talking about static methods, you don't need to create an object to use them. You can simply call them using the class name itself. Super handy for utility methods like calculations or conversions. So in simple terms, think of static as something that's class level. It exists once for the whole class, not once per object. Super useful, super efficient, especially when you want to share data or functionality across all instances. Let's break down this code and understand how the static keyword is working here. We have a class called circle, and inside it, we've defined a static variable called pi. Now, look at the main function. We are printing the value of pi using circle.pi directly with the class name. And that's possible only because pi is marked as static. If we didn't use the static keyword, Dart wouldn't allow us to access pi using circle.pi in the main method. We'd need to create an object just to get the value of pi, which doesn't make sense because pi is a universal constant. It doesn't change from one object to another. That's why we use static. It makes pi a class level property. It belongs to the class itself, not to any specific object. Then, we create a circle object with radius 5 and call the area method. Inside this method, we use the static pi to calculate the area. So overall, the static keyword helps us define values or functions that are shared across all objects and can be accessed without creating an object. Super useful for constants like pi. Let's now take a look at how static methods work in Dart with this example. We've created a class called calculator, and inside it we have two methods: add to numbers, multiply to numbers. But notice, both of these methods are marked with the static keyword. Now what does that mean? Well, by making these methods static, we're saying that they belong to the class itself, not to any specific object of the class. So when we go to the main function, look at how we're calling these methods. We use calculator.add 5, 3 and calculator.multiply 4, 6 directly with a class name without creating a calculator object. That's the power of static methods. They're perfect for utility functions or operations that don't depend on any instance variables. They just take some input and return a result. Now imagine if add and multiply weren't static. Then we'd have to create an object of calculator just to add to numbers. That's unnecessary and inefficient. So to summarize, static methods let you call functions directly from the class without creating objects. They make the code cleaner, faster, and are especially useful in cases like this: utility classes, helper methods, and constants. So, when should we actually use the static keyword in Dart? Let's break it down. Use static variables when you need a value that's shared across all instances of a class. Think about values like pi in a circle class. No matter how many circles you create, the value of pi remains the same. Or maybe you want to track how many objects have been created. A static counter variable would help you do that because it exists only once and updates globally for the class. This way, you avoid duplicating data in every object and make your program more efficient and organized. Now coming to static methods. Use them when the method doesn't need to access instance variables. In other words, when it doesn't depend on the object's unique data. Let's say you have a utility class for math operations like add, multiply, or something like string formatting or unit conversion. You don't need an object for those. Just call the method directly using the class name. This keeps the code clean and avoids unnecessary object creation. So, in summary, if it's a shared value or a utility function, go static. It makes your code more efficient, readable, and easy to manage. Let's understand a real-world example of static variable and static method in Dart. Here, we have a class called user. Inside it, we've declared a static variable user count. This keeps track of how many users have been created. And since it's static, it's shared by all objects. Each time a new user is created, the constructor increases the static count by 1. Then, we have a static method called showUserCount, which prints the total number of users created so far. Since it's static, we can call it directly using the class name. No need to create an object. In main, we create two users, Rohit and Dhoni. They both display their names, and finally, we call user.showUserCount to print the total user count. This is a perfect example of how static variables and methods can be used for shared class-level logic like keeping count or providing utility behavior. Let's see some important point related to static keyword. As you can see here, the warning comes. Next is only static members can be used inside static methods. Why we use const keyword? Saves memory as the value is stored once. Ensures the value doesn't change. Alright, let's do a quick recap of what we've learned about the static keyword in Dart. First, when we declare something as static, it means that the variable or method belongs to the class itself rather than to any individual object. So, you don't need to create an object of the class to access it. Second, static variables are shared across all instances of a class. That means, if one object updates the static variable, the updated value will be seen by all other instances as well. It's like having one common variable for the entire class. Third, static methods can be called without creating an object. You can simply use the class name followed by the method name. These methods are useful when the logic doesn't depend on any instance data. Fourth, we use static when we want to create constants, utility functions, or shared data. For example, mathematical constants like pi, helper methods like converting units, or tracking things like the number of users created. And lastly, keep in mind that static methods cannot access instance variables directly because they're not tied to any particular object. They only work with other static members of the class. So in short, static is perfect for situations where you need something that belongs to the class as a whole rather than to specific objects. Asynchronous programming. Let's understand why asynchronous programming is so important. Imagine you're building an app, and this app needs to fetch data from the internet, read a file from the disk, or maybe wait for some user input. Now, these kinds of tasks take time, a few seconds, or sometimes even longer. If your app just sits and waits for each of these tasks to finish one by one, your users will start to feel it. The app becomes slow, laggy, and unresponsive. That's where asynchronous programming comes in. Instead of waiting for one task to finish before starting the next, your app can start a time-consuming task, then immediately move on and keep doing other work while that task is still running. And finally, once the task is done, your app can handle the result. This makes your app feel faster and more responsive to the user. In Dart, we do this using something called a future. Futures are Dart's way of handling tasks that complete at a later time, like fetching data or reading files. So, asynchronous programming helps your app stay smooth and efficient, even when it's doing a lot behind the scenes. Let's talk about futures in Dart. So, what is a future? A future is just like a promise. It represents a value or an error that will be available at some point in the future. It's Dart's way of saying, hey, I'll get back to you later. When you start a future, you're beginning an asynchronous operation like downloading data, reading a file, or hitting an API. Now, this future won't give you a result right away. But once the task is complete, it will either return a result if everything goes well, or an error if something goes wrong. Let's take a simple real-world analogy. Imagine you're at a restaurant. You place your order. That's like starting a future. Now, instead of just standing there and doing nothing while waiting for the food, you go and do other things, maybe chat, scroll your phone, that's the non-blocking part. And finally, when the food arrives, you either get a delicious meal, everything worked perfectly, or the wrong order, something went wrong. That's exactly how a future works in Dart. You start a task, don't block the rest of your app, and once it's done, you handle the result, whether it's a success or an error. So first, we're importing the Async library. This gives us access to useful features like futures and delays. Now, the program starts and we print ordering pizza. This line simulates placing an order, just like starting an asynchronous task. Then, we use future.delathe to simulate a wait dot here. It's a 2-second delay. We are telling Dart, wait for 2 seconds, and then return a message saying pizza is ready. Now comes the then block. This runs after the 2 seconds. It receives the result, in this case, the message, and prints it out. So after a short wait, the app will show pizza is ready. We also add a catch error block. This is important. If anything goes wrong during the wait or execution, this block will catch the error and show a friendly message instead of crashing the program. And right after placing the order, we print another message, doing other things while waiting. This line runs immediately without waiting for the delay to finish. This perfectly shows how asynchronous programming works. The app doesn't pause or freeze while waiting for the pizza. It keeps going and does other work, then comes back when the task is done. This is what makes asynchronous programming so powerful. Your app stays smooth, responsive, and efficient. As you all saw, pizza is ready prints after 2 seconds. Let's change the time to 5 seconds. Now, you might have noticed, the message pizza is ready appears after a short delay. That's exactly what a future does in Dart. It lets the program wait for something to finish in the background without stopping everything else. Now let's pay attention to what just happened. You saw that the message pizza is ready was printed after a delay, not immediately. This is the true power of a future in Dart. It allows you to start a task, like fetching data or waiting for something, and continue running the rest of your code without waiting for that task to finish. In our example, while the pizza was being prepared in the background, simulated by a delay, the program moved ahead and printed, doing other things while waiting. Right away, once the task was done, the future completed and printed the final message. Pizza is ready. This is how asynchronous programming keeps your app smooth, fast, and responsive, by avoiding unnecessary waiting and using time wisely. Let's understand future chaining. In Dart, you can perform multiple asynchronous tasks in a sequence by chaining futures using the then method. This helps ensure that each task starts only after the previous one completes, maintaining a clean and readable flow. First, we define an asynchronous function that simulates fetching bread. It takes 1 second, and once done, it gives us the word bread. Next, we have another asynchronous function that adds filling to that bread. This also takes 1 second, and then returns a new string combining the bread with the filling. Now, to make the full sandwich, we call the bread fetching function first. When it's done, we pass the result, the bread, into the next function to add the filling. This is where we use the then method to chain the futures, so one task starts only after the previous one finishes. In the main function, we start by printing making a sandwich, which executes immediately. Then, we call the sandwich making function. Once the whole process is done, we print the final sandwich. And if anything goes wrong during the process, we catch the error and show an error message. Meanwhile, while all of this is happening in the background, we also print doing other things right away, showing that the app doesn't stop or freeze and can continue running other tasks. This is the power of asynchronous programming in Dart. You handle long-running operations step by step without blocking the rest of your app. And with future chaining, your code stays clean, readable, and organized. Let's understand how Dart handles errors when chaining futures. We begin with a function that simulates getting bread. It waits for 1 second and then successfully returns bread. So far, so good. Next, we have another function that's supposed to add filling to the bread. But instead of returning a value, it immediately throws an error. It simulates a failure, saying out of filling. Now, let's walk through the main execution flow. First, we call the function to get bread. Once it succeeds, we move to the next then block where we try to add filling to the bread. But here's the twist. Since the filling function throws an error, the next then block that expects the sandwich never gets executed. Instead, the flow jumps directly to the catcher block. This is how Dart's futures handle exceptions. If any part of the chain throws an error, it skips all remaining then blocks and goes straight to catcher. So in this case, what you'll see printed is just the error message, error out of filling. This shows how you can gracefully handle failures in a sequence of async tasks without crashing your app. The chain continues only as long as things succeed, and the moment there's a failure, it's caught and handled cleanly. Alright, so what's happening here? First, the app prints fetching user data. That's just to show the process has started. Then, we're calling a function that takes a couple of seconds to simulate loading some user information, like from an API. But the cool part? The app doesn't pause. It keeps going and prints, continuing with other tasks right away. That's asynchronous behavior in action. Your app stays smooth and doesn't freeze. Then, once the user data is finally ready, .then, block kicks in and prints user data loaded. And just in case something goes wrong during the fetch, there's a catch error, waiting to handle any issues and keep the app from crashing. So this is a great example of how futures keep your app running efficiently without waiting for every task to finish. Alright, let's quickly go over what we've learned about futures in Dart. First, a future represents a value that will be available later. It's like saying, hey, I'll get back to you once the task is done. Second, when that task completes successfully, we use .then to handle the result. It's our way of saying what should happen next. Third, if something goes wrong during the process, we catch and manage the error using .catch error. This keeps our app from crashing and helps us respond gracefully. Fourth, the biggest advantage of using futures is that they make our app non-blocking. While one task is waiting to finish, the rest of the app keeps running smoothly. And finally, we can chain futures using multiple .then calls when we want to perform tasks in a specific sequence. So with futures, we write code that's cleaner, more efficient, and responsive, just what we want in any modern app. We're going to make our asynchronous code simpler and cleaner using async and await. So now let's talk about async and await. These two keywords are game changers in writing asynchronous code. Instead of chaining multiple .then calls, which can get messy and hard to read, async and await let your code look clean, simple, and more like traditional step-by-step code. So what does async do? Well, when you mark a function with async, you're telling Dart, hey, this function is asynchronous, and it's going to return a future. Now comes await. You use await inside that async function to pause execution until the awaited future completes. It's like saying, hold on, Wait right here until this task is done, then move to the next line. No more tangled dot then, chains. Just readable, straightforward code. And all the power of asynchronous programming. That's async and await in Dart. Simple, elegant, and super effective. Let's break down this code and understand how async and await are working here. First, we have a function called fetchOrder. It's marked with the async keyword, which means this function will return a future. Inside it, we're simulating a delay of 2 seconds, like waiting for an order to be prepared and then returning the message order is ready. Now, let's look at the main function. Notice that it's also marked as async. Why? Because we're going to use await inside it, and Dart only allows await inside async functions. The first line prints placing order to the console. Then comes the line. String order is equal to await fetch order. What's happening here? This line is pausing the execution of the function. It's saying wait until fetch order is complete, and once it returns the value, we store it in the order variable. So after 2 seconds, we get order is ready, and that message is printed to the screen. Finally, we print enjoy your meal. So what's the magic here? We didn't have to chain dot then or set up callbacks. Our code looks clean and flows from top to bottom, just like synchronous code. But it's still non-blocking and asynchronous thanks to async and await. And that's the beauty of it. Simple, readable, and powerful. Let's see a real-world example simulating an API call. Alright, let's break down this code and understand how async and await are working here. First, we have a function called fetchOrder. It's marked with the async keyword, which means this function will return a future. Inside it, we're simulating a delay of 2 seconds, like waiting for an order to be prepared and then returning the message order is ready. Now, let's look at the main function. Notice that it's also marked as async. Why? Because we're going to use await inside it, and Dart only allows await inside async functions. The first line prints placing order to the console. Then comes the line. String order is equal to await fetch order. What's happening here? This line is pausing the execution of the function. It's saying wait until fetch order is complete, and once it returns the value, we store it in the order variable. So after 2 seconds, we get order is ready, and that message is printed to the screen. Finally, we print enjoy your meal. So what's the magic here? We didn't have to chain dot then or set up callbacks. Our code looks clean and flows from top to bottom, just like synchronous code. But it's still non-blocking and asynchronous thanks to async and await. And that's the beauty of it. Simple, readable, and powerful. Let's see how to handle errors using try-catch. Alright, let's walk through this code and understand what's happening with error handling in an asynchronous function. We have a function called fetchData, and it's marked with the async keyword, which means it returns a future. Inside it, we're using future.delayed to simulate a network request that takes 2 seconds. But instead of returning data, we're throwing an exception after that delay, mimicking a failed API call. Now, let's move to the main function. This is also an async function because we're using await inside it. The first line of main prints fetching data to the console. Next, we use a try-catch block. Inside the try, we call fetchData and wait for it to complete using await. Since fetchData throws an exception after 2 seconds, the control goes straight to the catch block, and the error message gets printed, error, exception, failed to fetch data. Then we have another print statement, app continues running. Now, here's what's really interesting. If you look at the output, you'll see that both the error message and app continues running appear after a 2-second delay. That delay is caused by the future.delayed call in fetchData. So, even though the function throws an error, the app doesn't crash. It catches the error gracefully and continues running. This is exactly why we use try-catch with async and await to handle failures cleanly in asynchronous code. Let's see how to run multiple async functions sequentially. Here we've got 2 functions here, make coffee and make toast. Both functions are marked with the async keyword, which means they return a future and allow us to use await inside them. In make coffee, we simulate a 1-second delay using future.delayed, and then we return the message coffee is ready. Similarly, in make toast, we wait for 2 seconds before returning toast is ready. Now, let's move to the main function. This one is also async because we're going to await the results. First, we print making breakfast. This happens instantly. Then we await make coffee. So, the program pauses here for 1 second, and once the coffee is ready, we print the message. After that, we await make toast, and again, the program waits here for 2 more seconds before printing that the toast is ready. Finally, once both tasks are done, we print breakfast is served. So what's happening overall? Even though these are asynchronous tasks, using await makes them run one after the other, just like synchronous code, but without blocking the main thread. It's clean, easy to read, and the output flows exactly like a real breakfast preparation would. This is the power of async and await in Dart, simple syntax, readable flow, and non-blocking execution. Alright, now let's take it 1 step further. Previously, we were making coffee first, then waiting for the toast. But what if we want to prepare both at the same time? Yes, let's make them run in parallel. In the main function, we start by printing starting breakfast. Then, instead of awaiting each function one after the other, we use future.wait to run both make coffee and make toast simultaneously. Future.wait takes a list of futures and waits for all of them to complete. So now, both coffee and toast are being prepared at the same time in the background. Once both are done, we use a simple for each to print each result. First the coffee message, then the toast message. And finally, we print breakfast is ready. And here's the cool part. You all must have noticed that the last 3 lines of output, the coffee, the toast, and the breakfast is ready message all appear together after just a seconds. That's the magic of running asynchronous tasks in parallel using future.wait, faster execution and cleaner code. Now let's understand how we can send emails one by one using async and await. We have a function called sendEmail, which takes a recipient name, waits for 1 second using future.delete, and then prints a message saying the email has been sent to that person. In the main function, we've got a list of recipients: Virat, Dhoni, Rohit, Sachin, and Sehwag. We then use a for loop to go through each recipient. And here's where the magic of await comes in. Inside the loop, we call sendEmail with await. That means it waits for the current email to be sent before moving to the next one. So, it sends to Virat, waits for 1 second, then Dhoni, waits for another second, and continues this pattern till all emails are sent. Finally, once the loop is done, we print all emails sent. So in total, this process takes about 5 seconds, because we're sending emails sequentially, one after another. Perfect when the order of operations matters, and when each task depends on the one before it. Alright, let's wrap things up with a quick recap of what we've learned about async and await. So first, async makes a function asynchronous. That means it allows you to perform tasks that take time, like fetching data, waiting for a response, or reading a file without freezing the rest of your app. When you mark a function with async, it always returns a future, even if it eventually gives you a simple value. Second, await pauses the execution of that async function until the future is complete. So you can literally say, wait here until this task finishes, then move on. This makes your code feel synchronous, it's cleaner, easier to read, and avoids deeply nested then chains. Third, use try-catch for error handling in async code. Since things can go wrong, maybe the internet is down or a file doesn't exist, wrapping your await calls inside a try block helps you catch and handle those errors gracefully without crashing your app. Fourth, you can run tasks sequentially or in parallel based on your needs. If one task depends on the result of another, you wait one after the other. But if two tasks can run independently, like making coffee and toast, you can run them in parallel using tools like future.wait. And finally, this approach is way cleaner and easier to manage than chaining multiple then calls. Your logic becomes straightforward, readable, and much easier to debug. So, async and await, super powerful tools for writing non-blocking, efficient, and modern Dart code. Let's dive into streams in Dart and understand how they help handle continuous data over time. So, let's talk about streams in Dart. Streams allow us to work with a sequence of asynchronous events over time. Think of it like a pipe that keeps delivering data little by little as it becomes available. Now, unlike futures, which give us just one value and then they're done, streams are different. They can keep sending multiple values over a period of time. And this is super useful when you're dealing with real-time data like chat messages, sensor readings, or live stock market updates. So why exactly do we need streams? Well, imagine trying to handle a continuous flow of data using futures. It wouldn't really work. Futures are great when you're expecting one value, like fetching data from an API once. But when you're expecting a series of updates, that's when streams step in. They help you listen to changes as they happen and react to them in real time. That's the power of streams in Dart. Now let's talk about the two main types of streams in Dart and when to use them. First, we have single subscription streams. This is the default type of stream in Dart. You can think of it like a one-time delivery. It can only be listened to once. As soon as a listener subscribes, the stream starts sending data. If you try to add another listener, it'll throw an error. This type of stream is best suited for operations like reading a file or handling a single HTTP request where only one consumer is needed. The second type is the broadcast stream. This type of stream allows multiple listeners at the same time. It's like a live radio broadcast. Anyone can tune in, anytime, and receive the data as it comes in. Broadcast streams are perfect for UI events like button presses or real-time updates where different parts of the app need to listen to the same event source. So remember, use single subscription streams when only one listener is expected. Use broadcast streams when you want to notify multiple listeners. Understanding the difference will help you structure your code more efficiently in real-world apps. Let's take a look at this example to understand how streams work in Dart. We've defined a function called numberStream, and it returns a stream of integers. Notice the syntax, async asterisk. This tells Dart that this function will return a stream and emit values over time. Inside the function, we're using a for loop that runs from 1 to 5. For each number, there's a delay of 1 second using awaitFuture.delay. Then we use the yield keyword to send out each number into the stream. So what's happening here is, instead of returning all the numbers at once, we're sending them out one by one with a delay, just like a timer ticking every second. Now in the main function, we call numberStream and assign it to a variable called stream. Then we listen to the stream using .listen, and inside that, we simply print the received value. So when this program runs, you'll see the output, each printed 1 second apart, because the stream is emitting values asynchronously over time. This is a simple example of how streams let you handle a continuous flow of data in Dart. Let me know if you want this formatted for a slide as well. In this example, we're generating a stream of numbers from 1 to 5 using an async asterisk function. Each number is delayed by 1 second using future.delay and then emitted using yield. In the main function, we listen to this stream. But before that, we use .map to transform each number into a string like number 1, number 2, and so on. Finally, .listen, prints each transformed value as it arrives. This shows how we can use streams to handle asynchronous sequences and use map to format or modify the data before using it. Let's talk about broadcast streams in Dart. By default, a stream in Dart can only be listened to once. This works fine for simple cases, but what if you want multiple parts of your app to listen to the same stream? That's where broadcast streams come in. A broadcast stream allows multiple listeners to subscribe to it. It's really useful when you're dealing with shared events like UI interactions, live data updates, or app-wide notifications. To create one, you simply convert a regular stream using the .asBroadcastStream method. So, whenever you need to share data with multiple listeners, use a broadcast stream. In this code, we're defining a function called numberStream, which uses stream.periodic to generate a new number every second. It emits values starting from 0, 1 at a time, and stops after sending 5 values thanks to the .take method. Now here's the important part. We want multiple listeners to receive the same stream of data. By default, Dart streams only support a single listener. So, we convert it into a broadcast stream using asBroadcastStream. Once it becomes a broadcast stream, we add two listeners, both listener 1 and listener, to start receiving the data simultaneously as it's being emitted every second. So in the output, you'll see both listeners reacting to the same values in real time. This is how you use broadcast streams when you want to share a stream of events with multiple subscribers. Let's talk about stream management in Dart and how streams power real-time updates in our apps. Streams for real-time data updates. Streams give us a way to handle continuous data flows, which means our app can respond to changes as they happen, whether it's a live feed, sensor data, or user interactions in real time. Using listen. To start receiving data from a stream, we use the listen method. It sets up a listener that waits for new data and responds whenever something new arrives. Error and completion handling. It's important to manage what happens if something goes wrong. That's where onError comes in. It helps us catch and handle any issues. And when the stream finishes sending data, ONIN tells us the stream has completed. Stream transformations with map. We can also transform stream data using the map function. This lets us change or format the incoming data before it reaches the listener, giving us more control and flexibility. Broadcasting streams. By default, a stream can only be listened to once. But if we need multiple parts of the app to listen at the same time, we convert it into a broadcast stream. That way, multiple subscribers can receive the same data without conflicts. We've already covered Dart's type system earlier, so let's quickly recap what we've learned. Dart is a statically typed language, which means it checks types at compile time, helping us catch errors before the app even runs. We use common types like int for whole numbers, double for decimals, string for text, bool for true or false values, list and map for collections. You can explicitly declare a variable's type like int age is equal to 25, or let Dart in for the type using var or final. So overall, Dart's type system makes your code safe, predictable, and much easier to maintain. So, we've seen that Dart has a strong type system. We can define variables as int, string, bool, and so on. But here's the thing. What if we're working with collections like list, map, or even our own custom classes, and we want to specify what type of data they should hold? That's where generics come into the picture. So in short, the type system tells what a value is, but generics tell what types are allowed inside a structure or component. Generics allow you to write code that works with multiple types while still making sure everything stays type safe. In other words, your code becomes flexible, but without losing the benefits of Dart's type checking. Rather than writing the same function or class for each data type, you can write one generic solution that works across different types. Simple, reusable, and safe. Let's talk about why we use generics. Type safety. Dart catches type errors at compile time, not at runtime. So if you accidentally pass in the wrong type, your code won't even compile. And that's a good thing. Code reusability. You write your logic once and use it with any data type, integers, strings, custom objects, anything. And finally, cleaner code. You avoid repetition, reduce the need for typecasting, and your code becomes easier to maintain and understand. In short, generics make your code safer, more reusable, and a lot cleaner. And they're an essential part of writing scalable Dart applications. Let's go through what's happening here. I start with a list that contains mixed types, a string, a number, and a Boolean. Then, I use a loop to print the length of each item in the list. As soon as I run this, Dart throws an error. That's because not every item in the list has a .length property. Strings do, but numbers and Booleans don't, and that causes the error. To fix this, I comment out the original list and rewrite it using a generic type. I specify that this list will only contain strings. Now, since every item is a string, Dart knows that it's safe to call .length on each one. When I run the code again, it works perfectly. So, by using generics, I make the code more type-safe, avoid runtime errors, and keep it clean and reliable. Now let's understand how generics work with a class in Dart. We start by defining a class called box, and notice the T next to it. This is a generic type parameter. It means the box class can work with any type that we specify later. It could be int, string, or even a custom class. Inside the class, we declare a variable content of type T, and we initialize it through the constructor. Then we have a method called displayContent, which simply prints the value of the content. In the main function, we create two boxes. The first one, int box, is a box int. It stores an integer 123. The second one, string box, is a box string. It stores the string Hexagon. We then call displayContent on both, and it prints the values inside each box. So, the key takeaway here is, by using generics, we've written a single class that works for multiple types while still keeping it type-safe and reusable. Now let's look at another great use of generics, using multiple generic types in a class. We've created a class called pair, and this time it takes two generic type parameters k, v. Here, k represents the type of the key, and v represents the type of the value. Inside the class, we have two variables key and value, which are initialized through the constructor. Then we have a method display, which simply prints the key and value in a nice key-value format. In the main function, we create two instances of the pair class. Pair 1 is a pair string int, where the key is a string age and the value is an integer 25. Pair 2 is a pair int string, where the key is an integer 1 and the value is the string Dart. We then call the display method on both pairs, and it outputs the data accordingly. So, using multiple generics like this makes your class more flexible and reusable across different data types, and all without compromising on type safety. Now let's look at how we can use generics with functions. We have a function called printlist, and notice the angle brackets T right after the function name. This means the function is generic. It can accept a list of any type. Inside the function, we take a parameter called items of type list T. That means the list can be a list of integers, strings, or even custom objects, anything, as long as we define the type when calling it. We then use a simple for loop to print each item in the list. In the main function, we call printlist int and pass in a list of integers 1, 2, 3. Then we call printlist string and pass in a list of strings a, b, c. So with just one generic function, we are able to reuse the same logic for different types of data. And that's the real power of generics. Now let's explore generics with class constraints in Dart. We start with a base class called shape, which has a method called draw. This method is meant to be overridden by other shapes. Next, we define two classes, circle and square, and both extend the shape class. They override the draw method to print their own specific messages, drawing a circle and drawing a square. Now, here's where the generic constraint comes into play. We create a generic class shapeDraw T extends shape. This means the type T must be a subclass of shape. So we can't just pass in any type. It has to be something that inherits from shape. The shapeDraw class has a method called render, which simply calls the draw method of the shape it holds. In the main function, we create two instances: circle draw using shapeDraw circle and square draw using shapeDraw a square. When we call render on each, they execute the overridden draw method from their respective classes. This approach makes your code both flexible and safe. You can use any shape as long as it extends the shape class. Perfect example of generic constraints in action. Let's now take a look at some of Dart's built-in generic classes, the ones we use almost every day without even thinking about it. First up, we have list T. A list is simply a collection of items of the same type. By specifying the type inside angle brackets, like list int or list string, Dart ensures that only values of that type can be added. This makes your code more reliable and prevents type-related bugs. Next, there's set T. A set works similarly to a list, but it doesn't allow duplicates. Again, we specify the type to make sure the set holds only consistent data, like set string for a group of tags. Then we have map k v. This is used when we want to store data in key-value pairs. For example, map string int could represent subjects as keys and their marks as values. Here, k is the type for keys and v is the type for values. Finally, there's future t. This represents an asynchronous operation that will eventually return a value of type t. So if a function returns a future string, Dart knows the result will eventually be a string, even if it comes after a delay. So to wrap it up, these built-in generic classes, list, set, map, and future, help us write type-safe, reusable, and clean code, while also giving Dart the flexibility to work with any kind of data. Let's take a moment to recap everything we've learned about generics in Dart. White heavy checkmark first, we explored what generics are and why they're so important. Generics allow us to write code that can work with different data types while maintaining type safety. Instead of writing the same logic multiple times for different types, we create a single, reusable solution. This not only saves time, but also prevents runtime errors by catching type mismatches at compile time. White heavy checkmark then, we looked at how to create generic classes. We built examples like box T, which can store any type of value, and pair K, V, a class that holds a key-value pair. These examples showed how generic classes make our code cleaner, reusable, and more flexible. White heavy checkmark next, we moved on to writing generic methods. We wrote a method like printlist_t, which can take a list of any type and print its items. This demonstrates how generics help us perform actions on data without worrying about the specific type involved. White heavy checkmark lastly, we introduced the concept of bounded generics. This means we can restrict a generic type to a certain base class. For example, using T extends shape ensures that only subclass of shape can be used. This approach improves type safety while still giving us flexibility. So overall, generics help us write robust, reusable, and safer code, making our Dart applications more scalable and efficient. Let's talk about one of the most important features introduced in Dart, null safety. Before null safety, variables in Dart could accidentally hold null values even when we didn't intend them to. This led to unexpected runtime errors, especially when trying to access properties or methods on a null object. But with Dart's null safety, those risks are significantly reduced. Null safety means that variables can't contain null unless we explicitly allow them to. This gives us more control and reduces the chances of our apps crashing due to null reference errors. Next, we have non-nullable variables. These are variables that must always contain a valid non-null value. If we try to declare such a variable without initializing it, the compiler will give us an error. This ensures that we don't accidentally leave important data undefined. On the other hand, nullable variables are variables that can hold null if needed. We indicate them using a question mark. For example, string name. This tells the compiler that the variable may or may not hold a value, and we'll handle that appropriately in the code. Dart's compiler also performs compile time checks. This means that any potential null-related issue is caught while we are writing the code rather than showing up later during execution. These early warnings help us fix issues before they become real bugs. And finally, all of this leads to enhanced code reliability. With null safety, our code becomes more predictable, easier to maintain, and less likely to fail unexpectedly. It helps enforce correct usage of variables across the entire project. So, in short, Dart's null safety is not just a nice-to-have feature, it's a major step toward building robust, error-free applications. In Dart, understanding the difference between non-nullable and nullable types is crucial for writing safe and reliable code. Let's start with non-nullable types. These types are considered safe from null, which means the compiler ensures they will never hold a null value. This makes your code more predictable. And the answer is yes, non-nullable types must be initialized. If you declare a non-nullable variable, you have to assign it a valid value right away, or you'll get a compile time error. This requirement helps prevent a whole class of bugs caused by uninitialized variables. Now let's look at nullable types. These types are the ones that can hold a null value. You declare them using a after the type, for example, string name. Because nullable variables can be null, they require null checks before you access their properties or use them in expressions. This is Dart's way of making sure you're consciously handling the possibility of a missing value. So in summary, with non-nullable types, you get safety and simplicity, but you must always provide a value. With nullable types, you get flexibility, but you have to be cautious and handle null cases properly. The key takeaway here: choose types wisely to ensure safer Dart coding. Decide whether a variable truly needs to hold a null value, and if not, keep it non-nullable for better code reliability. Let's briefly go over 3 scenarios to understand Dart's null safety. First, I declare a string variable and give it the value Hexagon. Since it's non-nullable, Dart is happy, and it prints Hexagon without any issue. Next, I try declaring the same non-nullable variable without a value. Dart immediately flags this as an error because every non-nullable variable must be initialized. Finally, I modify the declaration to make the variable nullable by adding a question mark. Now Dart allows the variable to hold null, and when I run it, it prints null. This progression shows us how Dart ensures safety by requiring non-nullable types to always have a valid value, while nullable types give us the flexibility to have variables that can be empty. Alright, let's start with a simple example. I declare a variable name as a non-nullable string and assign it the value Hexagon. Then, I print name.length. Everything works fine. Dart has no problem here because the variable is non-nullable and already initialized. Now, let's make a small change. I remove the value and just write string name. Notice I also add a question mark to make it a nullable string. Then I try to print name.length. But this time, Dart gives an error. Why? Because name is null by default, and I'm trying to access a property on a null value that's not allowed. So, how can we fix this? One way is to use the null assertion operator, the exclamation mark. I update the print statement to print name.length. Now I'm telling Dart, trust me, name is not null. But the truth is, name is null, and this causes a runtime error. So the takeaway here is, even if you mark a variable as nullable, you have to be very careful when accessing its properties. Always make sure it's not null, or handle it safely with conditions or null-aware operators. In Dart, non-nullable variables must be initialized at the time of declaration. If you try to declare a variable without assigning it a value, like a string, it will throw a compile time error. To fix this, Dart provides the late keyword. This tells the compiler, I promise I'll assign this variable before using it. Using late allows you to delay the initialization while keeping the variable non-nullable. This way, your code can run smoothly without errors. So here I've declared a nullable string variable called name. At first, I didn't assign any value to it. So when I printed it using the null-aware operator, Dart gave me the fallback, Hexagon. Let's update the same variable and assign it the value hello. Now when I print it, since name is no longer null, it simply prints hello and skips the fallback. That's the power of the null coalescing operator. It checks for null and gives you a default only when needed. Alright, so here I've got a nullable string variable called username, but I haven't assigned it any value yet, so it's null. Now, I'm using the is equal to operator, which means only assign this value if the variable is currently null. Since username is null at this point, Dart assigns it the value hexagon. And when we print it, yep, it shows hexagon. This operator is super handy when you want to set a default value only if nothing's been assigned yet. Let's quickly go over some of Dart's null safety features. First up, nullable type marked with A. This allows a variable to hold a null value. For example, string, name, next, the non-null assertion, using. This tells Dart, I know this value isn't null, so go ahead and use it. But be careful, if it is null, your app will crash. Then we have late initialization with the late keyword. This is used when you want to declare a non-nullable variable, but assign it later. Just make sure it's definitely set before using it. Now on to the null coalescing operator, which is, it gives you a fallback value when something is null, like var x is equal to name, guessed, and finally, the null-aware assignment, written as is equal to. This one sets a value only if the variable is currently null. So for example, username is equal to hexagon. These tools together help you write safer, more predictable Dart code. Let's quickly recap what we've learned about null safety in Dart. So, what is null safety? Simply put, null safety makes sure that you don't run into those dreaded null reference errors when your app is running. It prevents null issues at compile time, meaning Dart checks everything before your app even runs. It also ensures that all your variables are initialized before you use them, so you don't accidentally try to use something that's not set yet. This all leads to safer and more reliable apps. Now, why is this important? First, it helps you catch bugs early in the development process. Instead of running your app and finding issues later, null safety makes sure you're good to go before you hit run. Second, it makes your code cleaner and more readable. This is a huge benefit for you and your team, especially in larger projects. And lastly, null safety boosts your app stability and performance, ensuring a smoother experience for users. So, to wrap it up, null safety is a powerful tool that helps you write better, more reliable code. It reduces bugs, makes your app more stable, and helps your code stay clean and easy to maintain. Enum, short for enumeration, sealed class, reflection, extension methods, file handling, and networking. Let's start with enum. So, what is an enum? An enum, short for enumeration, is a special data type used to define a fixed set of named constant values. Instead of using plain strings or numbers throughout your code, enums give you a clear, predefined set of options. Now, why should we use enums? First, they improve readability and type safety. You know exactly what values are allowed, and the compiler can catch mistakes early. Second, they replace magic strings or random integers that are hard to track or prone to typos. And lastly, enums make your code easier to maintain. If you ever need to change or expand your set of values, you do it in just one place. So, enums are a great way to keep your code clean, safe, and organized. This is how we create an enum in Dart. We start with the enum keyword, followed by the name. In this case, it's weather. Inside the curly braces, we define a fixed set of named values: sunny, cloudy, rainy, and snowy. These are constant values and help us avoid using raw strings or numbers for such cases. Now let's look at the main function. Here, I'm using a for loop to go through all the values of the weather enum. Weather.values is a built-in property that gives us a list of all the enum values. Using weather.values.length, we get the total count, and with weather.values, we access each value one by one. So when we run this code, it prints sunny, cloudy, rainy, snowy. This shows how easy it is to work with enums and how they improve code readability and safety. Let's take a look at how we can use enums with conditional logic in Dart. Here, we have an enum called weather with 4 values: sunny, cloudy, rainy, and snowy. In the main function, we create a variable today and assign it weather.sunny. Now, using an if condition, we check if today is sunny, we print it's a sunny day. Otherwise, we print better grab an umbrella. So when we run the code with weather.sunny, we see the sunny message. But now let's change it. I update the line to weather today is equal to weather.rainy. This time, the condition fails, so the else block runs and we get the output: better grab an umbrella. This is a simple example of how enums make conditions more readable and meaningful by replacing arbitrary values with clear names. Now let's take enums to the next level by adding properties and methods to them. Here, we have an enum called traffic light with 3 values: red, yellow, and green. But notice something special. Each of these enum values has a duration associated with it. Red stays for 30 seconds, yellow for 5 seconds, and green for 25 seconds. To make this possible, we declare a final property duration and then use a constant constructor. Const traffic light this dot duration. This constructor assigns the duration to each enum value. We've also defined a method called display inside the enum, which prints a simple message like red light stays for 30 seconds. Now coming to the main function. In main, we simply call traffic light.green.display. This tells Dart to access the red light enum and run its display method. The result? A clean, structured way to associate data and behavior with enum values. This makes your code more readable, reusable, and powerful. Let's talk about sealed classes in Dart. A sealed class is a special type of class that restricts which other classes can extend or implement it. This gives us more control and safety in our code, especially when we know all the possible subclass in advance. So, why should we use sealed classes? First, exhaustiveness. Since the compiler knows exactly which subclass exists, it can help us catch missing cases, especially useful in things like switch statements or state handling. Second, it's perfect for state management or whenever you're modeling a fixed hierarchy of types like different UI states or API responses. And third, it prevents unwanted subclass from being created somewhere else in your app, so your architecture stays clean and predictable. In short, sealed classes bring structure, safety, and clarity to your Dart code. So here we're exploring sealed classes in Dart with a simple shape example. We start by creating a sealed class called shape. Now, what makes it sealed is that it restricts which classes can inherit from it. This means only specific subclass defined in the same file are allowed. This helps us build safer, more predictable code because we know all the possible types that shape can be. Next, we define two specific shapes, a circle and a square. Each of them holds its own property. The circle stores a radius, and the square stores a side length. Now we have a function that takes in a shape and figures out what kind of shape it is. If it's a circle, we calculate the area using the radius. If it's a square, we calculate the area using the side. We then print out the result. In the main function, we create one circle and one square, and we pass them to our area printing function. Based on the shape, it prints out the correct area. The beauty of this approach is that we're using sealed classes to tightly control the types and type checking to safely work with those types. It's clean, clear, and avoids bugs from unexpected subclass or misuse. This is a great setup for building robust systems like UI states, form validation, or anything where you want to define all possible types upfront. In this example, we're working with a sealed class called shape and two of its subclass, circle and square. Now here's the important part. We want to describe each shape differently based on what kind of shape it is. For that, we use a switch statement, and this is where the real power of sealed classes comes in. So let's walk through what's happening. We define a function called describeShape, which takes a shape as input. Now, because shape is sealed, the Dart compiler already knows all the possible subclass. In our case, it knows that shape can only ever be a circle or a square. That's why we can use a switch case statement with confidence. We're not guessing, and we're not writing defensive code. The compiler ensures we handle every possible type of shape. Inside the switch, if the shape is a circle, we extract the radius and print a message like circle with radius 5.0. If it's a square, we extract the side and print square with side 4.0. And here's why this is better than using traditional if-else conditions. First, the code is more readable and expressive. Second, the compiler will actually throw an error if we forget to handle any subclass of the sealed class. And third, it gives us full confidence that we've covered all possible types, no surprises at runtime. In the main function, we simply create a circle and a square and pass them into our describeShape function, and each one is handled correctly based on its type. So using switch with sealed classes is a powerful combination. Perfect when you have a fixed number of types and want your code to be safe, clean, and future-proof. In this example, we're modeling a user authentication state using a sealed class structure in Dart. Let's break it down. We start with a sealed class called authState. This acts as the base type, and only specific subclass are allowed to extend it thanks to the sealed keyword. That gives us full control and allows the Dart compiler to enforce exhaustive checks later. We define three different states the user can be in. Logged in, this class stores a username and represents a state where the user is logged into the app. Logged out represents when the user is signed out. Loading indicates that some authentication process is in progress, like logging in or checking credentials. Now, let's look at the function handle authState. It takes an object of type authState and then uses a switch statement with pattern matching to determine which specific subclass it's dealing with. If the state is logged in, it extracts the username and prints a personalized welcome message. If the state is logged out, it shows a simple message that the user is logged out. In the main function, we call handle.state with different states. First with loading, so it prints loading. Then with logged out, and it says you are logged out. And finally with logged in, Virat, and we get the output. Loading, you are logged out. Welcome Virat. There's a slight change I made. Earlier the username didn't have a defined type. Now I've added final string username to make it more type safe and clear. In Dart, we have something super useful called extension methods. They allow us to add new functionality to existing classes without actually modifying those classes. It's like giving extra powers to a class that already exists, whether it's a built-in type like string, list, or even your own custom class. Now, why would you want to use them? Well, first, they're great for adding utility methods, like trimming a string, formatting a number, or doing something custom with a list. Second, it keeps your code clean and modular. Instead of writing helper functions everywhere, you simply extend the class directly. And most importantly, you don't need to create a subclass or touch the original class. Just use an extension and you're good to go. So, extension methods are perfect when you want your code to be neat, reusable, and expressive without changing the foundation it's built on. Alright, let's look at a practical example of an extension method in Dart. We've created an extension on the string class and called it string extension. Inside this extension, we've added a new method named capitalize. What does it do? Simple. It capitalizes the first letter of a string. So if the string is empty, we just return it as is. Otherwise, we take the first character, convert it to uppercase, and then add the rest of the string using substring 1. Now in the main function, we have a regular string, Hexagon. We call a new method capitalize on it, just like it was built into Dart, and it works. The output is Hexagon with the first letter capitalized. This is the power of extension methods. We didn't touch the original string class, but we added our own custom functionality to it, making the code cleaner and more expressive. Let's try out extension methods on integers. We've created an extension called int extension on the int type. Inside it, we added to custom getters. Is even number to check if the number is even, and is odd number to check if it's odd. So first, we test it with the number 8. And the output is exactly what we expect. 8 is even? True. 8 is odd? False. Nice and simple. Now, let's change the number to 9 and run it again. And this time, it says, 9 is even? False. 9 is odd? True. So our extension is working perfectly. We've successfully extended the functionality of the int type, keeping the code clean, readable, and easy to maintain. In this example, we're extending the functionality of the list class with our own custom method, shuffleList. We start by importing Dart math package because we need the random class to perform the shuffle operation. Then, we define an extension called list extension on list t. Inside that, we create a method shuffleList that randomly rearranges the elements in the list using the Fisher-Yates shuffle algorithm. Now in the main function, we declare a simple list of numbers 1, 2, 3, 4, 5. We print the original list, then call our custom shuffleList method on it. And finally, we print the shuffled result. Every time we run this, the list gets randomized, thanks to our powerful little extension. This is a clean way to add utility to existing classes without modifying the original list class itself. Perfect for reusable, modular Dart code. Let's talk about extension methods with generics in Dart and how they can make your code more reusable and powerful. In this example, we've created a generic extension on list. That means this method, print elements, can work with any type of list, whether it's a list of numbers, strings, or even custom objects. Inside the method, we simply loop through each item and print it. Nothing fancy, but the power lies in the fact that it works with any list type thanks to the generic. In the main function, we test it with two different lists, one list of numbers and one list of names. Both of them call print elements, and it works perfectly because the method doesn't care what type of data it's printing. This is the real advantage of combining extension methods with generics. You write the logic once and use it anywhere on any data type without duplicating code. Simple, clean, and type-safe. Let's talk about a very important limitation of extension methods in Dart. They cannot access private members of a class. Here's what's happening. We have a class called user, and inside it, there's a private variable called _private name. That underscore means it's private. It can only be accessed within the same library. Now, we try to create an extension on user, and we want to access that private variable using a getter. But here's the catch, this won't work. Why? Because extension methods live outside the class, and Dart protects private members from being accessed externally, even by extensions. So if you try to run this, the compiler will throw an error saying something like, _private name is a private member and can't be accessed. The key takeaway here, extension methods are powerful, but they respect Dart's encapsulation rules. Private is private, and extensions are not an exception. Keep that in mind when designing your classes and extensions. And that's a wrap on the Dart series. Thanks for watching. Do like, share, and subscribe to our channel.